All right. So, hello everyone. So welcome to the Grand Challenge session, the morning session, the Interhemispheric Asymmetries associated with the high latitude forcings. So I would like to thank you for all your attendance on behalf of all the conveners. So the first thing is the introduction. So let's welcome you for give a short introduction. Yeah.
First, welcome to the session and good morning. I don't have too much to say since I already gave a tutorial. The only thing I would like to emphasize is, if you have any idea, no matter it's criticism or encouraging or future collaboration, you're more than welcome to talk to me or our team. Would love to collect comments and suggestions as well. Let's first welcome Zhang. And meanwhile, we only have 10 minutes for each speaker. And Qingyu, you will give to 2-minute reminder. That means you're supposed to ramp up and go to your conclusion quickly. Thank you.
All right, so today I'm going to just show some multifaceted aspect of ionosphere-thermosphere system response to a geomagnetic storm. I will using this, again, the 2015 St. Patrick's Day storm as example, because this is a near equinox event, and so we can at least minimizing the possible seasonal effect on the hemisphere asymmetries. So here's the IMF conditions for the day, and the second panel is the DST, then the bottom three panel cross-pole potential drop, hemisphere integrated Zhu heating, and auroral energy dissipation. Two curves here. The black curve is for the northern hemisphere integrated values, and the dashed red line is for the southern hemisphere. So even though this is a rather intense storm, you can the main part of the storm, the second stage of the expansion phase, is more intensive, starting after about 20 UT, and during that period, IMF BZ almost is constantly southward, and the BY, though, has some changes. But if you look at the energy dissipation in terms of both geoheating and auroral precipitation, for the majority of time, the energy input into the two hemispheres rather compatible, except a few places, northern hemisphere seems large. But on the average, just look at it roughly, the energy dissipation is roughly the same in terms of total energy into the hemisphere, and the seasonal effect is small. So, what we're trying to illustrate is how other effects might be also affecting the thermosphere, the ionosphere-thermosphere differences. However, if you just look at total energy dissipation, it's not the whole story. What you really need to do, the spatial distributions are also important. So I will illustrate that point by choosing 3 different UT times, 14, 20, and 22. For the 14 times, you do see that the BY is strongly positive, BZ is negative. However, there's some small excursion of northward during that time. And then for the other 2 times, in the BY, BZ is relatively stable. So here's the 14 UT time patterns. The top row is northern hemisphere, bottom is the southern hemisphere. This is the potential, the ionosphere convection pattern. This is the energy dissipation, energy flux, and this is Zhu heating. So if you just so the magnitude is slightly different, little bit higher potential drop in the northern versus south, and the energy dissipation by auroral precipitation are about the same. It's very close, and however, there you can see the large, very different spatial distribution with the northern hemisphere. The auroral distribution mostly on the downside, whereas on the in the southern hemisphere, dusk in the pre-midnight sector. And for the Joule heating, although the magnitude is about 100 gigawatts difference, but the total magnitude is also large. But you can see the northern hemisphere heating is mostly on the day side and downside, whereas in the southern hemisphere is mostly on the night side. Partly this is due to the difference offset between spin X, the geographic pole and the magnetic pole Qingyu mentioned earlier this morning. And here's for 20 UT time. Again, even though the BY, BZ are stable northward for the BZ is southward, but the BZ is positive. But if you look at the convection pattern, these two hemispheres are also very different, even though the cross-apart potential drop, they are similar. Similarly, for the energy dissipation, there are large differences, even though they maybe in the geomagnetic coordinates, they look similar. But again, because of the offset between magnetic pole and geographic pole, since the neutral atoms are mostly guided by geographic coordinates, so as a result, it still have a large difference, hemisphere differences. And similarly, for the 22 UT, similar stories. So what I'm trying to emphasizing is not only just total energy dissipation into the hemisphere is important, but also spatial distribution, how the energy, where and which latitude, longitude, latitude, those dissipation takes place also has to important impact into the ionosphere system response. Okay, so here's the three some plots and showing the thermosphere neutral mass density at 450 kilometers about the swarm A and C altitude. By color, then I don't know whether back. You can see the neutral winds at also the same altitude by the vectors. And the bottom panel shows the TEC from the simulations. So during this, as I mentioned, and during this time, BZ almost steady, southward, remains southward. But if you look at the TECs, you can see starting from a more or less symmetric, at least with geomagnetic coordinate, geomagnetic mid-equators, they are similar structure. Then you go to large hemisphere differences between, at least between northward equator or southward equator, then going back to a little bit slightly similar. And if you look at the neutral mass density response during the storm, they are also very, well, more asymmetry than symmetry at any longitude or for the any times in general. So symmetric conditions are rare. Asymmetric conditions happens all the time, seems like. So, and we are not just saying, this is just a model simulation. We do try to validate our models with the TEC. So in general, we do in the regions where TEC measurements, GPS measurements are led. So I think we did the simulation reflects quite well with the observations. So these are some following times at the 21 and the 22 UT again. So during this period, as storm evolves, you can see the large changes in overall TEC, global TEC distributions. So besides the TEC or PC changes, you will also see the neutral atmosphere, or especially the column density for O2 and 2, also the neutral thermosphere in terms of composition also changes response to the storms. So here's the comparison between GUVI and the TIGGCM at about for that event, the local time for GUVI is about 10:20 local time. So in general, you can see that as during the main storm phase, the depletion in the southern hemisphere into much lower latitude compared to northern hemisphere. Similarly, also reflected in the TIGCM simulations, because GUVI only expanding exampling every 90 minutes or so. So if we have a higher cadence, like GCM every 5 minutes for the same local time, so you can see more detailed changes of composition changes. So if you, here is the TEC along the same local time slice. If you're comparing the top panel composition change with TEC, in some places you have a enhanced TEC, and you also see increased O2N2 ratio. However, there's in some regions where TEC composition is increased, and you also have reduce the TEC in the region. So the correlation between new atmosphere response and the ionosphere electron density, they are not always one-to-one correspondence. So these are other UT times, other local sectors from the model simulations. So you can see that large local variations in addition to latitudinal variations. So this is, for example, at the dusk, 18 UT, and this is the midnight, and this is in the morning sect. In the morning sect, although you have increased the O2N2 ratio near equator, but in general, if anything changes, is a depletion of electron density. So, and another thing is that because, so for those steady plots, you don't really can see the TAD, TID very well. However, if you're using low-pass filters, you can see those features much better. This is, again, at the 10 UT, 18, and the midnight. So those TADs in the difference O2N2 ratio, and the bottom row shows the TIDs from differential TCs. So there seems, you can see equator propagating of TAD and also variations of TID. However, if you compare it with TAD and the TIDs, there are, the bottom panel shows the cross correlation between these two parameters. So their positive is their positive value when one means they are totally correlating, and the negative one is anti-correlating. So it's all over the map. There's no coherent changes, correlations between TAD and the TID. Okay, so I hope I get some major points crossing here. So what I say as also emphasizing what you already mentioned this morning. So hemisphere asymmetry in the IT system is the norm, whereas the symmetric behavior is the exception. The total hemisphere energy input between the hemisphere, even though they're symmetric, but that does not tell the whole story. So the local energy dissipation also plays a very important role in driving the asymmetric response in the IT system. And mostly important because the internal process, such as electrodynamic, chemical interaction between ion neutrals, are very, very important, and which is the part we really don't understand very well, and maybe hopefully GDC with concurrent neutral ion measurements will give us more ideas. So this is really the main part of, if we want to make progress in this aspect, we really need to do lots of work, and hopefully with the GDC measurements. And finally, I want to get this point really across is the correlation relation between TAD and TID is very complex, even though they both are manifestation of internal gravity waves driven by the energy dissipation in the atmosphere. But although they are the same manifestation from different parameters, but their relationship really we don't understand at all. So these are also we need a further understanding in the future. Okay, thank you.
All right, so thanks for the nice presentations.
Thanks, Gang. This is really interesting, particularly the last slide you showed the correlation between TAD and TIDs. Yes, I think the ionospheric response to the neutral disturbances will take time. So if you look at the correlation with time delay, that probably will improve the correlation.
Yeah, good point. So I did try different ways, try to correlate. So doesn't matter how you do different time lag difference, and some regions, they are correlating well, some regions, they totally off. So it's not just a single time lag will solve the problem. It's not only time lag problem. It's more than that.
Just two simple questions. I guess two items that need to be considered, right, as you're doing these kinds of studies. I guess you're starting to do it. I guess the first one is the easy question, which is, how to identify what of the differences are due to the sort of well-known BY effect, right?
Yeah.
That actually you and I wrote a paper on that, I think 30 years ago or something, 20 years ago or something. And the other, much more difficult, I guess, would be, you've got your potential patterns, and the potential patterns, I guess, are, your fits based on the available data. And of course, that's strongly dependent upon where you have data and echoes on the superdarn. So like how much of your asymmetries are asymmetries in data coverage versus asymmetries in reality, I guess, is a tougher one.
Yes, absolutely. So that's I showed that in some places you can see the northern hemisphere energy dissipation larger than the southern hemisphere. So it is true partly of this asymmetry in the AMI analysis is due to the data coverage. Yeah, so I'm not saying that everything is ground truth here. I'm just saying from the observation we have on the simulation tool we use for this event, that's what the system look like.
All right, so in the interest of time, let's move on. Thanks, Gang, again. So next speaker is Marc Hairston from UT Dallas.
All right. Being challenged here. That's the, okay. And what green is for? Okay. Have to make sure I know how to use the mechanics here. Thank you for having me. This is work that we're doing for the Living with the Star grant with Yu Jun is the PI here at UTD. And what we're looking at is how the penetration electric field behaves during storms. So let's see. Okay, there we go. When you have a geomagnetic storm, of course, the electric field in the polar cap expands equatorwards during the beginning of the storm and ultimately retreats back. This electric field drives zonal flows in the ions, and so we can use the data, the zonal flow in DMSP, to measure that. And this is the traditional way that we've done that, where you're just simply looking, these are orbits after orbits here, and you're looking at the flow, and you can see how far equatorward the excess flows penetrated, moved. One of the things I realized in the years of working with this is that there is a background flow to the mid-latitude flows in the zonal flows in DMSP. And so what I wanted to do was the thing where you looked, instead of just how far did it reach, but take the quiet time model and then do a subtraction of the storm day from the quiet time, and that would give you a better estimate of how far equatorward the flow, the penetration field, extended. Okay, what? Okay, there we go, okay. So this is some work that I showed last year at AGU and at CEDAR, just to show you the process of this. This is the the March 2013 St. Patrick's storm. And so what you've got first is just the background, the quiet time flow. There's not a whole lot of structure to this, but you will see that some of the other quiet times do have more structure. This is quiet. This is the storm day. So now you see the individual spokes for each satellite pass. This is in geographic longitude, geographic latitude. And this is just one leg. This is the dusk side afternoon leg of F16. These two are on a 500 to minus 500 scale, so you can see the small scale flows. This is the difference, and now it's on a plus 1500, minus 1500 scale, so now you can see the difference. So you can see that the first few flows, the first few legs are white because there's no difference. And then the storm comes, and now you can see how far equatorward the field has extended. Okay, so this was just the results from last year for the March 2013 storm. On the day side, we could see that there was a difference between the north and the south extent of the penetration field. Well, 20, 30 years ago when I started with this, everyone said, oh, well, it's going to be symmetric. And I kept thinking, no, this doesn't look like it in the data I've looked at. So you do definitely see a difference between the north and south. This is afternoon, sunset. And then on the night side, on F18, they do match up. And so what we think is happening here, our working hypothesis, is that it's the daylight, that the daylight causing the conductivity. Conductivity is different on the day side and is the same on the night side, so that the two do indeed match up on the night side. So that's what I wanted to see. So we're doing the 2015 storm in order to compare that. Now, DMSP is the original constellation of spacecraft. GDC is going to be following on what we've done, but in 2013 and 2015, we had 4 spacecraft in orbit, and you can see the local times here. By 2015, the orbits have processed a bit. 15 has moved about an hour later, 16 has moved about an hour later, F17 has moved backwards in time, and F18 has moved slightly forward. So it's not quite apples to apples, but we're still getting about the same. So, oops. Okay, there we go. Okay, so again, thank you, Zhang, for talking about the 2015 St. Patrick's Day storm. You've seen this already. What I did was I took the 10 days prior to the storm to do the quiet model, and then I did the storm day, which goes down to here, and then part of the recovery day. And then this is the IMF, which I'll talk about here in a minute. Okay, so go through the pretty panels here, but again, you see that we've got the quiet time. This is northern hemisphere, southern hemisphere. You can see the noise here. This is because you're getting close to the poles, and so this is shows that the polar cap in the northern hemisphere is tilted towards the U.S. sector, the American sector, whereas in the southern hemisphere, the polar cap is more off-center and tilted towards Asia. So these are the quiet times, and then here's the storm day north and south and recovery day north and south. Let's see, move ahead. Okay, so, and then this is F18, which is on the night side. So again, it's not, again, you can see there's a lot more structure. It's also a lot quieter too, but the southern hemisphere has this, does have a pattern to it. And again, the storm day, recovery day in the north, storm day, recovery day in the south. Okay, let's move to the, so this is the difference. This is the key thing to notice, that here's the storm day. The first few legs here, and I've got them lettered so you can see that, are all white because the storm day flows are about the same as the quiet time flows. There's no difference. You see first that there's a little bit of penetration, then one leg that has almost none, and then you start seeing penetration. And the recovery day continues, and the penetration is roughly steady. The other thing here is you see this light red here. There seems to be excess westward flow. And when I first saw that, I thought, oh, great. What I'm seeing here is the dynamo flow. The neutral flow after the storm has now jazzed up the ions. And so you've got this excess flow that continues after the fact. But I don't see that very strongly in the other ones. So this is something I want to look at some more. So that's the northern hemisphere. Here's the southern hemisphere, same thing. The storm day and then the recovery day with data gaps, I apologize. We always get those. Okay, so F18, similar thing for the difference for the storm day, the recovery day, the storm day, and the recovery day. And again, because it is later in local time, the storm, or the dials start, if I'm reading out, that's my first one, A over here, going around, and then we repeat going around here. Okay, so real quick with the IMF, most of this seems to be driven by the IMF. Where we call the onset depends on whether you're looking at the change in the pressure or change in the IMF. In this case, what we're seeing, looking at BZ here, you see the change in speed here. Well, is that the onset where you see IMF, BZ goes north? Then you have a short southern, and then it goes north again, and then another longer, but still only about 2-hour southern BZ that goes north again, and it goes south, and it's like this for the rest of the day. until the beginning of the recovery here at the end of the day, and then it goes back to being close to 0. So it would be nice if it were just a simple step function and we could look at things clearly. Instead, we have kind of a mess here at the beginning, but we live with what the data brings us. So if you look at the difference in F16, which is, again, on the day side, okay, thanks. You've got, here's here's the sharp onset at about a little bit after 8. So you see there's a difference, then it turns northward, and there's a retreat in the penetration field. And then you have the steady beginning of the storm up to about halfway through the main phase, and then you start seeing a retreat in the northern hemisphere, whereas the southern hemisphere continues to move equatorwards, and then this is the beginning of the recovery phase, and then both of them are moving back poleward, but sort of in step. There's about a 10-15 degree magnetic latitude difference in the penetration between the two hemispheres. Again, this is on the day side or the afternoon. If we go to F18, which is on the night side, same beginning mess where you have the sudden, penetration, retreat during the northward, and then down. But for the whole day during the main phase, the two are almost in lockstep up until the recovery, and then they both start retreating. And there is a difference, but it's not as great a difference as what you're seeing on the day side. So to try and compare apples to apples, so on the left is F16 and 18 for the March 2013 storm, and then on the right is the March 2015 storm. So you see for the 2013, we had a penetration, retreat, penetration, so you have the W shape. And again, it's very close together on the night side. Similar thing here, although obviously the IMF is different. You have the penetration and then some retreat, but there is the difference here. In the night side, it's not quite as close, but it's much closer than what you're seeing on the day side. So again, what we think is the difference here is the conductivity. The day side, you have differences in conductivity between the hemispheres. On the night side, you don't. But remember, F18 has processed about half an hour towards the day side. So I need to check exactly, but I think actually where F18 is at its peak here is in daylight, but the legs are still in darkness. So that may be what's going on here. Okay, summary here. So the first two I've already talked, that basically there is a difference between the north and south penetration, between the north and south hemispheres. The night side one, F18, sees something similar, but it's not quite as close together on the 2015 storm as the 2013 storm. And I think that's, again, because the satellite's orbit has processed a little bit further, and part of it's in daylight. The last part here is that I'm still working on the F15 and F17 legs for this, and then ultimately we're going to do the dawn side as well. And the full plan for this work that we're doing with Living with the Stars, we want to put together a data set of about half a dozen or more of these storms where we've done this full analysis so that we can look at this and have a full data set to be able to say, here's what happens between the hemispheres based on IMF, based on conditions, based on season, things like that. So, okay, thank you.
All right, thank you, Mark. Any questions? Yeah, just take one question.
Hey, Mark, that
Hi.
was really nice.
Thanks.
Have you ever done any integrals of the electric fields to calculate potentials and then compare the potentials between the north and the south to see if they're the same?
That's one of the next steps. I am partway into a project with that. We had that capability way back on what we call SISSES 2 up through F15. These are the SISSES 3. We're having to redo the programming and whatnot to do that. So that's one of the things I'm going to be working on this summer is doing potential drops for the satellites as well. So that will be ultimately included in all of this.
All right, so in the interest of time, let's thanks Mark again,
Okay.
and we'll
Thank you.
move on. Yeah. So next speaker is Sneha Yadav, represent the Sheng Tian.
How do I come back? How do I come back?
Go back. It's red.
I see, okay. Thank you. So now let's talk about asymmetry or symmetry in aurora. So in particular, I will be giving some results or discussing some results on the simultaneous observations of auroral streamers in conjugate hemisphere and the associated in situ observations. So we know that auroral streamers are roughly north-south aligned narrow bands of auroral luminosity. They originate in the polar boundary of the auroral oval and they extend equatorwards. Now it is well established that auroral streamers are the ionospheric manifestations of busty bulk flows, aka BBF, also known as slow bust. And these two schematics here, they give a very good representation of our understanding of auroral streamers and how they are coupled to magnetosphere. So there have been studies on the conjugate observations of aurora in the past, and here is an example by CEDAR et al., wherein they have used two ASIs operating over Iceland and Sova, and they have shown that the generation of aurora in the opposite hemisphere is nearly symmetrical. Okay, so the previous studies based on the conjugate auroral observations can be broadly divided into two categories. One category deals with the in-situ observations that require two spacecraft in the opposite hemisphere. Here is an example, and here it has been shown that aurora can be very different in two hemispheres on few occasions. So this category, we have an advantage of very large spatial coverage, but then we have to compromise on spatial resolution. Then we have the second type that requires two ASIs operating along the same field lines in the opposite hemisphere. Here you see one example by Matoba et al., and wherein they have shown that auroral beads develops almost symmetrically in the opposite hemisphere. And this can be seen very clearly here in this lab. We can see that auroral beads develop almost symmetrically in two opposite hemisphere. And this suggests that the source of auroral beads are same and located near the equator. Now, why I'm showing this here is because in this study, we have used both in situ, that is polar satellite data, and ground data, that is all sky imagers, and ground magnetometer network to provide coverage in the two hemispheres. So these are the results, and in this panel, you see the polar data in the southern hemisphere. This is the Themis ASI's data in northern hemisphere. So basically here it consists of three ASIs. And here you see the ionospheric currents, which are derived from magnetometer data. And here this is the upward field line current, which are represented in a red color. Blue is the downward field line currents, and these dashed lines here, they represent the horizontal current. So you can see here that in all these multiple events observed on the same day, we have these kind of structures in the southern hemispheres, which are also seen roughly in the same location in the northern hemisphere. Of course, we cannot resolve these structures in the polar data because of low spatial resolution, but when we see in the northern hemisphere, we can resolve these structures. And these structures are indeed auroral streamers. And basically here we have group of auroral streamers which develop repetitively. Also, in correspondence to these streamers, we have the upward field line currents, which is something which is expected, but it's nice to see such correspondence in the observations. So this is another perspective of our auroral conjugate measurements, and here what you are seeing is the temporal evolution of aurora. That is, we have plot these with respect to time, and here this is magnetic local time, and this is magnetic latitudes. These are kilograms and these are evograms. And in the upper panels, we have the AE index, and based on the AE index, we identified 8 events of auroral events, which are highlighted by these dashed lines. And in these 2 bottom panels, we can see the local time evolution of auroral structures in the both hemispheres, and we can see that these structures, they evolve in time almost in a similar fashion, and these are highlighted by these dashed lines. Then we also see a very good correspondence with the upward field line currents here, which is also seen in these kilograms in the northern hemisphere. Okay, so this slide shows the predicted current systems of streamers. So we know that associated with auroral streamers, we have the pair of upward and downward field line currents, and also a pair of current loops, clockwise and anti-clockwise. So in our observations, we also observed streamers, upward and downward field line currents, and pairs of these counter-clockwise and clockwise horizontal current systems. So it's nice to see these patterns in the observations. Okay, so lastly, we have also studied the injection activities for all the auroral activities, and most of them are streamers. So this figure here, it shows all the available satellites, and this is the location of auroral activities in the MLT range. And here we have not shown GOES and LANN satellite data because we are still working on it. So we have just shown here Themis, all 3 satellites which are located here in the farther east of the MLT region of auroral activities. So here you see the electron fluxes from Themis E, D, and E.
Sneha, 2 more minutes.
Sure. We can see this for all 8 events of auroral activities. We have the enhancement in electron flux, and these are dispersed enhancement in the electron fluxes. In Themis A, which is situated in the further east of it, there is more dispersed enhancement in the electron fluxes. So this suggests that the injection region might be situated in the pre-midnight sector, and from there electron drift towards eastward, and that's why we see these kind of dispersed electrons in Themis E, D, and more in A, which is in the further east directions. Okay, so I think I will conclude now that we have observed auroral streamers which develop symmetrically in 2 hemispheres. We also observe the predicted current systems and also the electron injections in association with these auroral activities. Thank you.
All right, thank you, Sneha. So we have minutes for 1 more, 2 questions. So any questions, suggestions, comments?
All right. If not, maybe we can save to the discussion session.
Okay, thank you, Sneha.
Thank you.
Yeah, our next speaker is Aaron Ridley.
Okay. Laser pointer. Thank you very much. The last talk was actually a fantastic introduction. So in order to do interhemispheric asymmetry studies in the aurora, you basically have to go to extraordinary lengths to get aurora in both the northern hemisphere and the southern hemisphere. there was a time when image was above one hemisphere and polar was sort of obliquely looking at the other hemisphere. And so there are some events that you can look at, but they're not that common. And so what we wanted to do was propose a mission where you actually have two satellites that can view both auroras at the same time. And that's the MAX mission. So here's a reminder of the decadal survey goals. I'm going to zip through this. And so the MAX mission goal is basically determine how the magnetosphere-ionosphere-atmospheric coupling regulates energy flow through the near-Earth space environment. And so this addresses 3 of the 4 large-scale decadal survey goals. So this is, we haven't paid any high graphics people. So this is my drawing of the MAX mission here. So MMS taught us a fair bit about reconnection. Themis taught us a fair bit about what's going on in the tail. And MAX is going to be looking down on the polar regions to basically tell you how MMS and Themis are connected together. So the objectives of MAX is understand how the ionospheric conductance regulates energy flow from the solar wind through the magnetosphere-ionosphere system. Understand how the formation and evolution of night-side mesoscale auroral features, like what we just heard about, are regulated by ionospheric conductance, and predict the variations in the global aurora as driven by the solar activity. And we're going to do that by basically having 2 satellites in circular orbit, and they're going to be looking down on the northern hemisphere and southern hemisphere at the same time. They'll be orbiting at around 20,000 kilometers altitude. Okay, so objective 1, as a lot of text, basically, we want to look at how the open-closed field line boundary changes as a function of time when BZ turns southward, and looking at how the flux changes in the northern hemisphere and in the southern hemisphere when you have one hemisphere bathed in sunlight and one hemisphere in darkness. Objective 2 is talking about the night side, where we have mesoscale structures like we just heard about, and looking at how those mesoscale structures may be dependent on the conductances that exist, the conductance differences that exist on the day side. So looking at basically like what we just heard about. Objective 3 is basically, can we take all of these measurements and predict what the aurora is actually going to do? And the motivation for this is when we look at global scale auroral patterns, they look nothing like reality at all. And so we really would like to do a much better job of predicting, the thinness of the aurora and some of the structure in the aurora. And here's a movie, which it might be better over there with lower light. But basically, we took 24 hours of data. Whoa. 24 hours worth of data of model results. Let's go backwards and then let's go forwards again. And then you can see basically how the aurora behaves as we would observe it. And you can actually see some substorms go off and stuff like that. The northern hemisphere is red and the southern hemisphere is blue. And this is just showing one satellite. Then we can take this and we can look at what is the coverage in the northern hemisphere and in the southern hemisphere. And you can see that as one satellite observes the northern hemisphere and gets 100% coverage, the other satellite in the other hemisphere gets 100% coverage. And so if you look at are we measuring the aurora at all? And the answer is we measure the aurora for a while, and then we don't measure the aurora, and then we measure the aurora for a while, because both satellites will be near the equator at the same time. You can change the spacing of the satellites, and you can have both satellites basically like 90 degrees apart. So as one is setting, the other is rising. and you can view like the northern hemisphere for a long time, then the southern hemisphere for a long time, then the north. And then you can get continuous viewing of one aurora or the other aurora all of the time. We can do storms, but let's see if that will play. It doesn't look like it's playing, but it basically looks like the same, the last movie, but the edges get clipped because it's a storm. Oh, hey, there we go. So it will become brighter. Yeah, so you can see the storm going off, and you see the edge clipping of the aurora. But we measure the vast majority of the aurora during the storms, and so we won't be able to get the complete auroral oval during large geomagnetic storms. But you know, the vast majority of time we'll be able to get the complete aurora. And this shows the coverage, and you can see dropouts because of the edge clipping. Why not elliptical? Well, so elliptical orbits are really good because the satellite just sort of hangs up here for long periods of time and hangs down here for long periods of time, but then comes down, and you basically won't get any data while you're in this area, and the other hemisphere won't get any data while it's in this area. And so it's not great for that. And the other issue is that these orbits precess, and this will be down near the equator, and this will be down near the equator for long stretches of time, and then you won't get any measurements of the aurora at all. So circular is better for continuous observations of the aurora throughout time. Yeah, and so if this is up during GDC, we would basically get global auroral energy inputs during the GDC mission. Okay, so MAX is a proposal that we're writing right now. It ties together the science of MMS and THEMIS. It addresses decadal survey goals, and it's basically looking at the aurora, and it will help us understand the asymmetry in the aurora and energy inputs. Thank you very much.
All right.
Larry.
Yeah, of course. If you're measuring the aurora, you know I was going to say something.
Of course.
But yeah, this is really impressive. And you're going to see stuff over the polar cap too, I presume. What kind of observations? Do you have high sensitivity?
Yes, we'll be able to. So these are very similar to the imagers that are on ICON right now, which are derived from image satellite observations or imager. Yeah.
So you'll be able to see things propagating then from the day side to the night side.
Oh, absolutely.
So you'll be able to do a heck of a lot more than you just said, and much really important things, which is what drives the whole system and makes it work, which is the day side to the night side. So you can do a lot more than you're saying, much more.
Oh, absolutely. 100% agree that we will be able to. I mean, one of the reasons why I'm presenting this here is to offer you sort of a flavor of what the mission, the science objectives, but then there are a lot of other things that we could do with this type of data. Absolutely. Agreed.
So any other questions? If not, let's thank everyone again. And so next speaker is Naomi Maruyama.
Oh, okay. I can start. Oh, no. No, this is not mine. Okay. Anyway, yeah, I'm Naomi Maruyama from University of Colorado, and I would like to acknowledge my co-authors, which will show up here, George Kazanoff and Alex Grosser from NASA Goddard. And today I'm going to talk about the hemispheric asymmetry of the superthermal electrons, which is very different from our previous speakers, and their impact on the, oh, it's not coming in. Yeah, I continue. So the impact of the hemispheric asymmetry of the superthermal electrons on the energetics of the upper atmosphere, focusing on the electron temperature. Should I continue or? Oh, okay, okay. That's great. How do I advance a green button? Or am I? Oh. Okay. This green button.
Yeah, this one.
How?
Yeah, it's advanced.
Okay, okay, it worked. Okay. Okay. Great. Sorry about that. Okay. Okay. So yeah. So electrons in the ionospheric effusion from the textbook, heated primarily by photoelectrons and cooled by colliding with ambient ions and neutrals. And electron temperature negatively correlates with electron density because the energy transfer from the electrons to ions is proportional to the square of the electron density. So we are going to focus on this energy source, photoelectrons or superthermal electron in a more general term. So what are superthermal electrons? It's free electrons with the energy from 1 to 500 eV. And the primary source of the superthermal electrons in the Earth's upper atmosphere is the photoionization of the neutral atmospheric atoms and molecules by solar UV, as you already know. And the second source is the impact ionization from magnetospheric energetic particles as the secondary electrons, as previous speaker talked about. And superthermal electrons play an important role in generating the air glow emissions by interacting with upper atmosphere, as gold observation shows. Furthermore, heat flux is very important when calculating the electron temperature in IT models, which has been often neglected in the past years. And including the heat flux improves agreement with, I'm sorry, how do I give? Okay, sorry, here. I'm so bad.
The red button. Yeah, this is advanced.
Yeah,
This is backward.
yeah. Somehow, I'm not very. Anyway, okay, it's okay. So yeah, including heat flux improves the electron temperature, and because the increased temperature increases the plasma scale height, so it's important. So anyway, so we are going to address two science questions. First, what is the role of the hemispheric asymmetry in the formation of superthermal electrons in the coupled magnetosphere-ionosphere system? Second question, to what degree superthermal electrons originating from the conjugate hemisphere play a role in the energetics of the ionosphere and plasmasphere on the other side? And then how much of their energy can be lost in the magnetosphere and then get redistributed in the ionosphere and thermosphere system? So in order to address this question, we integrated two physics-based models, STET and IPE models. So what is STET model? It's a superthermal electron transport model developed by George Kazanov, solving for Landau-Boltzmann kinetic equations. And default state uses the center dipole approximation. Therefore, we tilted the dipole and evaluated how tilting the dipole impacts the hemispheric asymmetry of the superthermal electrons. So here I'm showing the photoelectron flux as a function of sorry. Okay. Energy up to 500 eV. And red is the original center dipole, and blue is the new tilted dipole. Okay. First, upward flux shown by the solid line are changed because the geographic location of the magnetic footprint and also the solar zenith angle by tilting the dipole. Secondly, the downward flux shown by the dashed line will also change because the superthermal electrons escaping from the ionosphere experience small angle scattering when traveling through the plasma sphere as a result of Coulomb interaction with the thermal ambient plasma, which is cooler than the superthermal electrons. We also included the effect of the diffuse electron precipitation caused by the Whistler mode chorus waves, which is a type of electromagnetic plasma waves with frequency below the electron cyclotron frequency. We evaluated how the tilting the dipole will impact the hemispheric asymmetry of the superthermal electrons caused by the diffuse precipitation. Here, notice that x-axis energy covers now up above 1 keV, which is different, much larger than the previous one. So first, small bulge here, created by the primary precipitating electrons, which is downward due to diffuse precipitation. Secondly, sorry, I'm very bad. Somehow, okay, it's okay. I can point. Okay, this secondary. Okay, you have better. Okay, the large peak here at lower energy are created by the escaping secondary flux and upwards shown by the solid line and return flux downwards shown by the dashed line. Both upward and downward flux are reduced by tilting the dipole. Okay, so this compares the superthermal electrons, including the photoelectron only on the left, whereas right-hand side includes both photoelectron and diffuse precipitation effect. And again, x-axis energy is different, but this comparison shows that the energy spectra of the superthermal electron significantly modified by including both photoelectron and the diffuse precipitation effect. Okay, so in addition to energy spectra, also heating rate from the superthermal electrons to the thermal electron is also changed by tilting the dipole. So we implemented the state heating flux into IPE and evaluated the impact of the hemispheric asymmetry of the superthermal electrons in the energetics of the upper atmosphere.
So Naomi, 2 more minutes.
Okay, yes, I can finish that. So IPE, in short sentence, is a global 3D time-dependent model of the ionosphere and plasmasphere. I need a magic. Sorry. Okay. And we coupled state and IPE, but there was some challenge because state is 1D kinetic model requiring a lot of computation, whereas IPE is a 3D global time-dependent model. So state needed to be simplified by using so-called plasmaspheric transparency approach. So plasmaspheric transparency is defined by the ratio of the number of particles leaving one end of the magnetic flux tube to the number of particles entering to the other end, which is T in this equation 1. This approach retains the pitch angle diffusion effect based on the original kinetic state code. Okay, so we calculated the plasma temperature for equinox first. First, notice that the state heating increases the plasmaspheric temperature by 1,000 Kelvin, whereas no change seen in the ionospheric electron temperature. This increased heating is caused by heating from the trapped superthermal electrons to thermal electrons due to Coulomb collisions. And here, hemispheric asymmetry in the heating rate in the ionosphere is caused by background atmosphere. Now we calculated the June solstice. Again, state heating increases the plasmaspheric temperatures. And here, now we see that ionospheric temperature is increased in winter hemisphere, which is southern hemisphere. I forgot to say that red is southern and blue is northern hemisphere. So southern hemisphere, shown by the red line, is increased due to the conjugate for the electron effect. And hemispheric asymmetry in the electron temperature is emphasized in this new coupled state IPE code, which is extended down to the ionosphere, like 200 kilometers. And we noticed that the electron temperature profile is determined by the combination between the heat conduction from the magnetosphere and also the photoionization from the different atmospheric condition down in the lower atmosphere, and also the cooling due to the ion cooling effect. Okay, summary. Do I have time for summary? Okay, thank you. Yeah. So hemispheric asymmetry of the superthermal electron depends on three things. First is the background neutral atmosphere at the magnetic foot points. And second, solar zenith angle. The third, pitch angle scattering due to the Coulomb collision with thermal plasma as superthermal electrons travel along the field line, and they sometimes become trapped due to the pitch angle diffusion. And secondly, hemispheric asymmetry of the electron temperature depends primarily on electron density below 500 kilometers, but whereas above 500 kilometers, electron temperature seems to be depending on the heat source, for example, photoelectron heating or other heating, such as the heating due to diffuse precipitation or ring current heating. And our study demonstrated that the coupled state IPE model significantly improves the hemispheric asymmetry of the heating rate and also the electron temperature by treating the trapping effect more realistically, which was not done in the original IPE model. And hemispheric asymmetry of the temperature is enhanced, especially for the June solstice case, and extending down into the ionosphere. This is my final slide. My next step is to calculate the impact of the hemispheric asymmetry on the air-glow emissions, and I have a poster this afternoon if you're interested in further discussions. Thank you very much. Sorry for the trouble.
All right, any questions? Okay, one quick question.
I have a bunch of questions, but I'll ask you one question. When you looked at the superthermal electrons from the other hemisphere, are you actually taking into account like the production rate also? So does the density change too?
Yes, so the state, actually I didn't explain. So there are two parts. So IP actually calculates all those processes. And separately, when we couple to state, I don't know if I have time to go back because it doesn't work. So yeah, the state also calculate the production and secondary production as well. Yeah, and then we couple the heating rate. Yeah, yeah, we can talk offline. Yeah.
All right.
Detail.
Thanks, Naomi.
Thank you.
Let's move on to the next talk given by Qingyu.
So hello everyone. So this is Qingyu from NCA. So today I'm going to talk about the interhemispheric asymmetries in terms of the ionospheric response during the 2013 St. Patrick's Day event. So I can't move. Oh yeah. So the 2013 St. Patrick's event received a lot of attention. However, so the ionospheric response during the mainstorm still not well understood. For example, during 17 and 18 not UT, So you can see American sector, in the American sector, there are lective storms, which is indicated by the reduction of the TEC in the typical ERA region. And also you can see there is a strong, and the negative storm effect in the southern hemisphere is stronger. So then it's the motivation of this study to study the inter-hemispheric ionospheric response during the main phase and low and middle latitudes. So the question is approached by a combination of data analysis as well as the simulation. So the data we are using are mainly the ground-based TEC data from the GNSS network. And the model we are using is the global ionosphere-thermosphere model. So particularly at high latitude, we use the AMI pattern to drive the GITR, so which is similar as the methodology Zhang used in her simulation work. So here shows the data model comparisons at a certain longitude in the American sector. So the top panel shows the differential TEC from the observation, and the bottom panel shows the differential TEC from the simulation. So basically, the simulation will reproduce the observations, although some differences exist. And particularly, the asymmetric lective storm phase indicated by the in the red box is well reproduced, with the southern hemisphere has stronger lective storm phase. So we actually did a term analysis, which is now shown here, to the ion continuity equation, which indicates that the neutral wind transport is the main contributor to the ionospheric response at this longitude during this period. So let's take a look about the formation of the lective storm effect at that longitude. Here shows the ionospheric response in the southern hemisphere. So as indicated by the red line here, so by the way, the top panel shows the density variations, and the bottom panel shows the meridional wind variations. So you can see significant TAD signatures in the neutral wind. So the right, on the right shows how the neutral wind affect the electron density variations. So in the top side, so you can see the neutral wind can drag the ion either downward or upward depending on the direction of the neutral wind. So at this UT, so the wind is poleward, so which drags down the electron density ions, so the electron density reduced in the top side. But you may notice that the scenario is quite complex and lower altitudes. So you can see an enhancement at lower altitude, which is probably due to the vertical shear of the meridional wind, which compress the ionosphere, which is adiabatic, and so the electron density increases. And the opposite is true for the 18 UT, which you can see northward, which is a more equatorward neutral wind disturbance. So here just compares the density, the electron density variations and the meridional variations at the conjugate locations along this longitude. So what you can see is that in the southern hemisphere, the electron density reduction is stronger than the northern hemisphere, which is associated with stronger disturbance neutral wind and southern hemisphere, while in the northern hemisphere, the disturbance neutral wind is weaker. So what's the cause for the different disturbance neutral wind at conjugate locations? So here just shows the meridional neutral wind at the same longitude as a function of universal time as well as latitude. So we highlight the longitude we are shown on the left by black lines here. So what you can see here is that you can see there are several TADs propagating equatorward from the high latitude in each hemisphere. So in the northern hemisphere, the TADs with the same polarity in the southern hemisphere, the TAD with same polarity meets roughly around at the latitude we are focusing on, while in the northern hemisphere, the TAD with the same polarity actually meets southward of the latitude we are focusing on, or even the TADs with the opposite polarity meet at the latitude we are focusing on, so which reduce the disturbance neutral wind in the northern hemisphere and cause the weaker elective storm phase in the northern hemisphere. And the difference due to in the TADs is mainly caused by the different distributions of TADs that also show in Gang's simulation. So at this local time, at this UT, the northern hemisphere has much stronger Joule heatings than the southern hemisphere. This is the same figure I showed earlier today. So to sum up, in this study, we found that the observed ionospheric response at 70 West in the American sector is well reproduced by GATEM. And we found that traveling atmospheric disturbance, the TADs are the most important contributor to the ionospheric response during this event at the longitude we are focusing on. And the asymmetric elective storm phase effect at low and middle and low latitude is mainly contributed by the differences in the interactions of TADs in different hemispheres. So more details can be found in my recent published paper. Thank you for your time. So any questions?
Any question, comments?
If not, let's welcome the next speaker, Yu Hong.
I'm so sorry. Thanks. So even I'm not an engineer, I know how to use this one. Hello, everyone. My name is Yu Hong from UT Arlington. This is my first time turn to the CEDAR in-person meeting. I'm talking about the inter-hemispheric symmetry of the magnetospheric forcing and its impacts on the IT system during a rainstorm event. And I would like to thank all the co-authors here for making this work possible. So first is the introduction. So as we know, the inter-hemispheric symmetry, or IHA, as shown in the right figure, hopefully you're quite familiar, the ion convection and particle precipitation can be highly symmetric during the storm events. And so why this matters? Because the IT system is highly affected by the two forcing. As shown in the bottom figure, the neutral density can be highly different between the two hemispheres during storm time. So that leads to our motivation. So first, the inter-hemispheric symmetry of the magnetospheric forcing are not fully understood. So what we do is use the realistic pattern from a model to specify the two forcing. And also the IHA has a symmetry in the IT system due to the magnetospheric forcing are not fully understood. So we will use this realistic pattern, the forcing, to driven GATEM for further study. All right. So a little bit of motivation. So we use data DMSP for the specific the cross-track ionodrift to the VY, and also we use gauge satellite normalize the neutral density. For model, we use GATEM to show the global response to this storm. And we use NCAR 3 dynamo as a global driver for the electrodynamics. And as we introduced, we use AMI pattern to specify the ion convection and particle precipitation, the two forcing. All right, so this first is the inter-hemispheric symmetry showing the magnetospheric forcing, the CPCPs. So, sorry, in the very top, we have the MF condition. So you see the MFBZ is listed almost 16 hours during this storm time as a constant value, almostly. And we have the BY perfectly first keep positive and then turn to negative during this storm event as shaded in the shaded area. And we use the symmetry index to quantify the symmetry between the two hemispheres of the CPCP here. So you can see we have also the average value of the two hemispheres. In the northern, we use the red color, and bottom, we use the blue color for the southern hemisphere. Clear symmetry can be seen from the CPCP, and in the very bottom, we use the symmetry index to see the time variation of the symmetry. So you can see the CPCP has a pronounced inter-hemispheric symmetry during the storm event, and the biggest value, maximum, can be over to 113%. And now let's look at the symmetry in the ional convection extension to lower latitude. So in the figure, we show the DMSP observation. Thanks for Mark's introduction. He showed how we find the boundary to the DMSP observation. And in the top, we use the red color for the northern hemisphere. In the bottom, we use the blue color for southern hemisphere. So basically, there were a lot of symmetry. So if you look at the top, the northern hemisphere, the dusk side, the satellite line just extend very low to low latitude. But for the dusk side, the dashed line, it doesn't change too much. And for the southern hemisphere, the blue color, you see the two lines is specifically the dusk side and the dawn side from observation. They just reversed between the BY positive and negative period. And also, you can see the two lines, the red line in the top and blue line in the bottom, connected by the arrow. It looks like quite similar, but they are for different hemispheres. To simplify, we summarize the lower end of the boundary for the two hemispheres and both for the dusk side and the dawn side to quickly show the symmetry during this process. So you can see, like for the positive BY period, the northern hemisphere has extension in the dusk side and contraction in the dawn side, while for the southern hemisphere is upside direction. And perhaps you also notice that for the northern hemisphere, inside the red box, the downside, which is the dashed line here, doesn't change too much. So what happened with this? We further checked the Gidim simulation result of the 2D pattern because we have more information in this figure. Also, in the top, we show the northern hemisphere. Bottom, we show the southern hemisphere. Is consistent with the linear figure. And the first column is the, so this 2D pattern is just a snapshot of the specific time. We call it BY positive, BY negative, the T1, T2. This is the meaning. And you can see for the northern hemisphere, it's changed less change in the northern hemisphere, while for the southern hemisphere, no matter the two sails, you see the orange color change from very hard to the lower, and the blue color enhanced from the two time periods. So this is actually the BY dependency of the two convection sails. While for the northern hemisphere, perhaps you also notice that the orange color, which is the downside sail, it doesn't extend to a lower latitude. Instead, it's extending in the middle night to the lower latitude. So this is the reason why we see less change in the downside, right? So perhaps this also suggesting us it's not enough to focus on the extension, only use the dusk and downside, because they also have some extension in the other side, other local time, I mean. Finally, a briefly conclusion is the ional convection extension also have significant inter-hemispheric symmetry. And they also have the storm and MFBY dependence in both two hemispheres, especially for the southern hemisphere, you can see here. And finally, we focus on the symmetry in the IT system. We look at the neutral mass density, the D rho. The two figures is just the same result, but the left one is for gauge observation, and the right one for Gidim simulated result. They focus on the dusk side. So some similar structure you can tell from this figure, like for the positive BY time, you have the northern hemisphere enhanced much earlier, like this, both the simulation and observation. And when the BY just reverse to the negative value, as shown by the vertical dashed line at this specific time, you see the southern hemisphere enhanced even much higher in the simulation result. Also, they have some like the similar structure, the TID structure, shown by the error. And to mathematically quantify the symmetry, we did this figure. So in the bottom is nothing new. We just take the average value of the top panel, the neutral density from the over 40 absolute value G latitude to see the time variation here. And in the right figure, we also add the simulation result, the inter-hemispheric jaw heating, to see the relation between the heating and the neutral density variation. And basically, you can see the northern hemisphere during the positive time enhanced much earlier, and after that, by turned to negative, the southern hemisphere enhanced or enhanced. Also, they see this originally from the heating we specified with Amy pattern, and you can see the density enhanced also attained from the two hemisphere, the polar region to the equatorial region. This is due to the ion convection extension, as we shown in the last slide. And if you just compare the relation between the Joule heating simulation result and the neutral density, something like the peak value we have here for the Joule heating, and several hours, 2 or 3 hours later, we find a peak value in the neutral density, also in the mixed value, the Joule heating, and then you find the neutral density. All right, they have some correlation here. So the both observation and simulation results still have clear BZ, which is storm and BY dependence, and they are affected by the magnetosphere forcing and Joule heating. And finally, it's a brief summary. So in this study, the magnetosphere forcing is specified by the Amy pattern, and the result used to driven GATM to see the global IT system response during the storm. So we found that firstly, for the forcing highlighted region, the forcing have a clear inter-hemisphere symmetry during the storm. And also of the ion convection extension, they also have strong storm and BY dependence, as shown by both the observation and GATM simulation. And finally, the IT system, they have some inter-hemisphere symmetry due to the storm, which can be highly affected by the symmetry in the ion convection and the extension, also the relative Joule heating. So I have a poster section this afternoon. If you have more questions or interest in this study, just feel free to catch me there. So I'm going to start here, so I'm ready to take questions. Thank you.
All right, thank you. Yeah. So any questions for you? All right, if not, let's move on. The next two speakers are virtual attendees. So the first one is Delores Knipp. So Delores, are you online? Can you hear us?
I am online. Can you hear me?
Yeah, we can hear you clearly. Yeah.
All right. I'm going to share screen.
Okay,
One
great.
moment. All right. Good morning, everyone. I wish I could be there, but several instances of travel prevented me from joining the group. So I will do my best to give you a very quick overview of the interhemispheric asymmetries and Poynting flux, some of which Alex Chartier mentioned this morning and also Yua discussed. So I'll give you a couple slides of background and then present results from the 3 space platforms where the interhemispheric asymmetry has been pointed out in the last 5 years of research or so, and then give you a summary. So bottom line up front, these low Earth orbit observations are revealing hemispheric asymmetries and Poynting flux. And as Alex mentioned, the percentages sometimes don't agree, but given that we have 3 or 4 platforms now showing this, there seems to be agreement that the Northern Hemisphere is receiving more Poynting flux. Since Alex gave a brief tutorial, I'll just note that the Poynting flux is the electromagnetic wave energy transfer, and in this case, it's the application. It's predominantly from the magnetosphere to the ionosphere, although I will show you one slide where there is upward Poynting flux that can be distinguished in the statistics. If you want to read a little bit more, there's a shameless plug for the summary for the chapter that we recently published, and Steve Kapler is the lead author on that, electromagnetic energy input and dissipation. Excuse me. And let's see, it looks like I am not fully sharing my screen here. Is that true?
Yeah, right.
No, okay, let me see if I can fix that.
We only see part. Yeah, it's good.
Yeah, there we go. Thanks. Sorry about that. Okay. So some background. There's been a lot of effort on trying to measure the quasi-steady Poynting flux from the last actually 3 to 4 decades. It was in the early 80s that Dynamics Explorer flew, and it took about 10 to 15 years to extract the data. Excuse me.
Go ahead. No.
Yeah, which Jim Gary did, and he showed by combining the northern and southern hemispheres that there were indications that in low activity there was Poynting flux in really coming into the cusp regions, and then when the activity went higher, it seemed to shift to the auroral zones. At the data out of Astrid published by Olson et al. In 2004 gave a somewhat similar result. They did have different boundaries on their activity sorts. So this was KP greater than 2, seemed to be showing up day side, but more auroral input then as well. There has also been a lot of effort on their very short fluctuation in alphanic Poynting flux. 6 years of polar data are shown in this graphic with non-storm on the left and storm on the right, downward Poynting flux on the top and upward Poynting flux on the bottom. And what you'll notice here is that there's a distinct day-night pattern and not so much, or a little less, at least in the storm times. And then if you go to storm time, there's still a very strong enhancement in the day side and then again in the night side in subauroral regions. So cusp and subauroral regions. So that kind of motivated some effort by Poynting et al. To check the swarm data for where might we find hemispheric asymmetries if they exist. And so it looks like we really need to be in a mode where LEO satellites are looking in day-night, ascending, descending modes. And that is exactly what Poynting et al. Did. They pulled data from 120 days in 2016 and 2017, February and November, July and March, where swarm was sampling mostly day-side and night-side locations. And these are not graphics from Poynting et al., it's what I've extracted. But basically what they were finding is if I have a plus here, that means that the northern hemisphere to southern hemisphere ratio is slightly positive, and that was true for all of 20 to 25 March 2016. Once we got more into the springtime, we started seeing stronger asymmetries, more than 10% preference for northern hemisphere to southern hemisphere. And then when we get into the summertime situations, we're seeing very large preferences for northern hemisphere compared to southern hemisphere Poynting flux in the alphanic input. So that pattern is going to continue. As I said, northern hemisphere dominates southern hemisphere. Only during the southern hemisphere summer, or i.e. northern hemisphere winter, do we get a dominant southern hemisphere Poynting flux. So there's a very clear difference here. I became interested in this work because of some work that Cheryl Huang published back in 2017, where she was looking at about 200 DMSP passes for high activity, intense storms. And she didn't really quantify this, but you can see northern hemisphere versus southern hemisphere. There seems to be, by eyeball, a different pattern. So Liam Kilcommons and I and Marc Hairston and Robin Coley started looking at processing a lot of DMSP data using only the quality 1 flags from the SISI's instrument. We came up with 9 satellite years of DMSP data, spacecraft in 3 orbit planes, and we have about 220 kilometer resolution in equal area bins. So our sampling is shown here. And then we wanted to maximize the coverage, so we looked at solar cycle 24 peak for the most part. You saw one of these, part of this graphics this morning. For low activity, northern hemisphere has more activity in the auroral zones, even for low activity, than the southern hemisphere. Both hemispheres have more Poynting flux than has quasi-steady Poynting flux than has been indicated by some of the previous event studies. And then if we go to higher levels of activity, we see that enhanced, and definitely the auroral zone Poynting flux tends to dominate. But what you see here is, even though we have a lesser coverage, about 2/3 coverage in the northern hemisphere, we're getting pretty high values compared to the southern hemisphere. And what I will do in a moment is show you how we try to normalize that. Again, there's an asymmetry in the Poynting flux in the northern hemisphere about noon, even if we take into account all of the IMF-BY variations.
Delores, it's 2 minutes. Yeah.
Yes. Pardon?
2 minutes left. Two minutes.
Delores, 2 more minutes. Then can you hear us? Issue. Internet. Yeah, it's not.
Willow.
Hello, I'm sorry for the internet problem. See how strongly we depends on the high tech now, our lab. When we are waiting for the talks and the speakers coming back, maybe we can have some discussion. Meanwhile,
So the Poynting flux asymmetry, in addition to what several speakers have shown with respect to the model results. So I think there's some exciting opportunities to address these questions with GDC and other upcoming missions. So thank you.
All right, thank you. So in the interest of time, let's move to the next virtual speaker and move all the questions to the discussion part. All right, so next speaker is Yongliang Zhang. So
thanks, Delores. Is that okay with you? You may move on move all the question part in the discussion. Hope you can stay with us.
Yongliang, can you hear us?
30 minutes? It's frozen.
Times KP greater than 3. I think there's some pretty strong indications that there are localized field-aligned currents. We're seeing that out of the analysis that we're doing with some Ampere data. So yes, I believe there is substantial.
Okay. So is that we are still in the room? Yeah, that's the Zoom link. So next speaker is Yongliang. So Yongliang, are you online? Yeah, we can see your slide, but we can't hear you. So are you muted?
Okay.
Okay.
Good. Yeah, I just want to show one example that the whole we can understand the hemispheric asymmetric in the stone time auto into thermosphere auto into ratio depletion. So before we do that, we know that the displacement between geomagnetic pole and the geographic pole could affect the asymmetric distribution of auto into. For example, this is the kind of quiet time auto into map and in the geographic coordinate, but you can still see in the southern hemisphere you have depletion in the highlighted in the Australia sector. Actually, we found that it's due to the magnetic pole location change. If we map it in a geomagnetic coordinate, what you can see is actually the depletion is more or less uniform over different longitude. Actually, I had a question to Delores just a moment ago. Said we always see alternating depletion in the pole cap. So I think that's indicated that always some energy input there. So this during equinox and even during kind of a winter or solstice conditions. So this kind of October time, and you can still, this is non-stone time, and you still see strong asymmetric, but actually if you map in the geomagnetic coordinate, you see more or less kind of a smooth distribution for the longitude. The gradient the small gradient from southern to northern is the season effect. So now let's go back to this famous superstone that many people studied before. We put here is the autoentry map from Groovy. Over 2 days, time goes from right to left. What you can see, the feature is that definitely it's symmetric. And before stone, it's kind of smooth over the different magnetic latitude. But once it goes to the end of November 20th, you can see the depletion northern hemisphere reach to the magnetic equator. But the southern hemisphere actually expand to the low latitude slowly. And until the mid of November 21st, then reach the magnetic equator. So this is strong asymmetry because we know this is the winter season, northern winter season. There's strong south to north wind. And that's mean they should have, it's easy for the southern hemisphere neutral wind, this is background wind, I say, from south to north that help to bring alternating depletion air process to equator. But this is not the case. Actually, the northern hemisphere, you can see have rapid down equator motion of depletion. So why is that? So we know the heating is in the high latitude, the source of the auto-N2. So that must be geoheating and the particle station is stronger in the northern hemisphere. Indeed, if we at the bottom plot we see here is the Groovy hemisphere power, because Groovy see auroral images, so we can calculate the hemisphere power. And the blue line is the northern hemisphere, HP, and the green line is the southern HP. You can see at the beginning of stone, they are mostly on the same magnitude. However, to the later of November 20th, you can see we see northern HP just double the southern SP. So that's indicated, that's coincident with this strong heating here. And so that's the indication of energy input from particles. We also run this AMI model to get the geoheating map. Indeed, at the top is the northern hemisphere from 16 UT to 1730 UT. What you can see that the strong geoheating here. Actually, the southern hemisphere at the bottom, the geoheating rate actually it's smaller, qualitative, let's say, smaller than the northern hemisphere. So that's confirmed that we have both particle precipitation and the geoheating come from is higher in the northern hemisphere than the southern hemisphere. That creates rapid equatorial moving of auto to depletion. However, later time, this is actually the asymmetry still lasts for a few couple more hours. And however, later of the day, the southern northern hemisphere actually is about same or even reversed. Actually, you can see here at the 1930, it's actually southern hemisphere start to getting larger. So that's the reason actually southern hemisphere auto to depletion keep moving toward the magnetic equator, while the northern hemisphere rapidly recover because this background wind is kicking in, taking effect there. So that's the idea. So why do we have this asymmetric energy input at high latitude? So we look at this IMF condition on day, this is November 20th. Note that what we see, the groovy data, O2N is around the local noon at 12. And the heating, because we know the O2N depletion happen on the night side or morning side, that with a lot of heating happens, and the correlated to day side. So even we see this O2N2 variation here around 18 UT, but to look back the source of IMF, so we have to go back to take care of remove the co-rotation time, for example, about 6 hours, and looking back at this from 11 to actually 13 UT IMF condition, what we can see was the dramatic difference is this very strong BY. BY is actually positive and larger than the BG, the absolute value of BG. So I think this may play a role because BY affect the convection pattern and the heating and all those things come together. But how this affect the particle position is still unknown. I think we need the kind of global magnetosphere modeling to help us to understand how IMF condition control the energy input. So here's a quick summary. You can see during November 2003 storm, we see strong O2N asymmetric depletion, and both the particle position and the Joule heating is asymmetric, and northern hemisphere is larger for a few hours. That related to the asymmetric, and there's a large positive dominant IMF BY is likely the source for both particle precision and the Joule heating asymmetric. Thank you. That's it.
All right. Thank you. Yeah. So maybe we can move on to the discussion box. So first, are there any questions for Yongliang? So if not, let's just go to the discussion part.
First, thanks all the speakers for the very interesting presentations. And we learned quite a lot from different aspects, observation and simulation as well. I would like to start the discussion session. Let's go back to the questions. Let's see. I listed for the first year. Here we go. So this is just the start of a grand challenge session, which will last for another 3 years. Oh, I'm not sure, it's including this year, yeah, probably 3 years. And so I would like to kick out this session with those questions. So first of all, what are the recent results and the resources available to address this question? We got some suggestions and comments during the break, like use the LiDAR, conjugated observation, and probably FPI and SuperDown. And if you have any other suggestions and comments, and feel free to raise your hand and let us know. Oh, Sheng.
Yeah, obviously GPS data is going to be very useful. We know we have data gaps over the ocean, but particularly for the American sector, North American and South American sector, we have pretty much very continuous coverage from North Pole to the South Pole. Qingyu's talk shows some of these results. But if you look at all the way to the north, 90 degrees, and all the way to the south, we still have a very nice coverage. So this will be a fantastic database for the hemispheric asymmetry studies. And we have that observation since 2000, around 2000. So far, we are doing some sort of statistics. For example, we can calculate the monthly average, because we have data every day, and we do the monthly average over solar cycles. So that could be a potential use for people to understand the climate orange. I think that's very important. You have a continuous coverage in latitude. That's going to be very useful for this project.
Thanks, Sheng. That's very important point indeed. I just wonder, if possible, we can combine the ground-based GPS observation with satellite occultation observation, which doesn't have the limitation of the, ground and the ocean.
Yeah, that's possible, but Cosmic 1, I think, survived for a couple years, and we have some overlap. But Cosmic 2, the new one, supposedly the data will be available that could be combined with ground-based GPS observations.
Right. Thank you. So anybody want to talk about gold observation? I think anybody has.
This is Yongliang. I'd like to mention that GUVI is still running, and even though we are looking down on the disk, but we have full spectrograph data information. And recently we just developed an algorithm to separate, because we know that 1356 emission from atomic oxygen has two components. One is the photoelectron impact on neutral, and the second is the O+ and the electron recombination. That means it carries ionosphere information as well as neutral thermosphere information. In the region equatorial arcs in the duskside, we see strong contamination in the auto-entry products. That's the motivation. We try to remove this ionosphere effect. So we use the 1304 and the 1356 radians together to separate those ionosphere and thermosphere contribution. Now we are able to get a beautiful equatorial arcs anomaly as well as a clean auto-entry map simultaneously. So this could be very useful because GUVI is a local times changing, right? So could be useful for this kind of study.
Well, that's very exciting. Thank you. Thank you for the information. Definitely, we like to follow in details. Does anybody want to come on ICON or GOLD or all the satellite coverage? So, Astrid, do you want to say something about the ICON capability?
It's well known. ICON mainly looks northwards, so it has data from -10 to 40 for the remote. But there are conjugate maneuvers, and I think, at least for the electrodynamics, that's very helpful to look at asymmetries. And also you can look at wind effects, and even though you don't measure both hemispheres, you can study asymmetry effects through that by combining it with other data, because you have the wind in the F region. So.
Thank you. Right. So maybe we should move on to the second question. What are the hurdles for making progress you would expect? And, for the ground-based, probably the coverage would never be totally symmetric. That's something we can think about. And for the simulation, probably Gang mentioned about, no matter what you do, you still see something asymmetry. So what do you think about it in terms of data simulation? Amy had represented the best capability in terms of specifying the high latitude electrodynamic forcing. So maybe you can comment on that.
Yeah. I think that the highlighted forcing definitely is one important driver for the hemisphere asymmetry. However, Amy relies on the data. If you don't have enough data cover both hemispheres or equally or in a comparable way, like Larry was mentioning that some of the asymmetry shown in Amy results maybe not just due to the data coverage. That's absolutely true. So Amy is data-driven. We need a expanding superdome, at least in the southern hemisphere. Bill, I'm a vote for him. So I think that especially it's difficult to, also bigger part of the southern hemisphere covered by ocean more than in the northern hemisphere. So lots of geophysical, geological, whatever, it's political, all these reasons affecting how the ground distribution, the observation availability, and what kind of instruments can be derived. But I think so ground observations, I'm just want to emphasize, is very, very important in addition to the space-based satellite measurements that they don't have these kind of geographic kind of limitations, but on the other hand, they are orbit by orbit to have a limited spatial coverage. So I again, with even as a model, I'm really emphasizing with the observers, and their contribution to this field is very, very important. So we basically have to eliminating what is, in order to understand what the cause is, maybe we one step at a time and say, take this one particular forcing and look at it and say if it is not important, then we look at the other. But I mean, it is a very, very complex problem. But another thing is, as I mentioned, that internal process probably also play more, if it's equal or even more important role in driving the different hemisphere asymmetry. So yeah, both internal and external driver need to be sorted out. And model alone, probably, model can certainly provide the insight, but you need observation to validate the model results. If without validation, you're just, daydreaming sort of way. Okay,
Absolutely.
sorry, I'm rambling too much.
I totally agree. Yeah. Go ahead.
I have two questions. One is about what other effects can we find due to the asymmetry? And the second is, can we quantify directly the different causes of the symmetry on the effects? Yeah.
That's a great question. First, you're talking about the physical mechanism. And in general, we have a rough idea. The mechanism can come either way, internally or externally. And that's actually the one of, how important or quantify their effect to the ionosphere-thermosphere. That's exactly the goal of a session. And hopefully we can answer, clearly in 3 years at the end of this Grand Challenger session. I don't know if we can do it, precisely and pinpoint to this mechanism cause which in-hemispheric asymmetry yet. That's actually the motivation for this session. But thank you for raising that question. And even for describing the in-hemispheric asymmetry, a simple index, like a symmetry index, that's not enough. I think Doya from the Magnetosphere, well, I think he's in Hawaii and having fun. Well, not that fun. But she proposed use a different way to even just quantify the symmetry. So that's something still, up in the air, and we need to discuss what's the best way to even quantify how asymmetry, how big is the asymmetry, and then we need thinking about, what's the strong physical connection with other possible forcing as well. Yeah. Thank you. Any other question and comment? If not, probably we should think about what is a realistic plan for the next 3 years, reachable plan. Okay. And no way we can build up never reached effort with GDC emission, which, it's going to cross finger for that. If we're lucky, we may get it launched in 7 years, but our session will only be 3 years. And so what we can do, what I think is a more practical goal for us and to achieve for this session. I don't know if anybody want to throw a couple of ideas? Yeah, that's probably true. Right. I just throw the question and keep maybe something, you can do some brainstorming and let us know. And like well, the next item actually I already mentioned. We need to think about what's the best way we can even characterize asymmetry, not just the point. How about 2D or 3D? Is there any other way we can characterize to include more information in terms of spatial distribution and temporal variation and all those informations when we talk about asymmetry? And the last item is we would like keep our mind open and we would love to collaborate as many people as possible. We want to build up a sub-community or subsection and to focus on this topic if you're interested. I know somebody approached me already, and I'd love to hear more comments and more suggestions. Probably we can keep communicate with each other either way through email or Tanicon, or and also you're more than welcome to join the next session as well. And Sheng, do you want to comment something?
I just want to make a quick comment because the asymmetric or asymmetric is really a complicated thing, and our IT system is also very complicated. So as Zhang just mentioned, so we emphasize the drivers. The drivers in two hemispheres could be different. On the other hand, we also need to emphasize the internal process. That's also Zhang mentioned. I did not know whether you have mentioned about, for example, the equatorial ionization anomaly. That's one of a good example whether these two anomalies, two crests, are asymmetric. This is also potentially a good topic. And that is, of course, is an external process, right? Has nothing to do with highlighted drivers. The other thing maybe including those irregularities, whether the bubbles have some asymmetric around the magnetic equators. So I think the system is complicated, and including many aspects, ionosphere and thermosphere and coupling will be also important.
That's very true. Yeah, MIT coupling definitely. You will play very important role to produce asymmetry in both high latitude, mid and low latitudes as well. You mentioned about the equatorial anomaly. The crust could be quite asymmetry due to either way the internal process like neutral dynamics or seasonal variation or even penetration in electric field and neutral dynamos, and all those processes definitely play roles. And the challenging here is we may not be able to pinpoint this variation is caused by this mechanism by 50%, by another mechanism 30% or something like that. That's definitely it's difficult. And but the modeler can help if we got a precise information of the forcing, and the internal mechanism absolutely is important. The ionosphere-thermosphere coupling, that's probably something we can do in terms of model improvement or model data comparison. See how the internal process can be represented by the model as well.
Delores actually has a comment for the Poynting flux. So Russell Cosgrove has a new Poynting flux that can reflect the inter-hemispheric asymmetries on CCMC. That's just from the chat.
Oh, can you read it, please?
So Delores wants to tell you that the Russell Cosgrove put his new Poynting flux asymmetry model out at CCMC.
All right, thank you so much. So definitely we can run this model publicly, through the CCMC, and then maybe we can do model data comparison with that, use that framework, use that platform as well at the CCMC. And all right, so it's almost 12 o'clock, and thank you so much for everybody for attending the session, and see you in the next session in the afternoon. We are continuously discussing this topic, but the focus will be more on the no atmosphere driven asymmetry. Thank you. Enjoy your lunch.
told me I was crazy, yeah, but I still thought that maybe she'd show up. Oh, but now I'm dodging potholes in my sunburned Silverado, like a heartbroken desperado, headed right back to my roots. Something about the way she gets me tells me she loves Eastern Tennessee, yeah, but all I brought back with me was some sand in my boots. Yeah, but all I brought back with me was some sand in my boots.
It's been forever, my dear, but I can't stop here, 'cause I know where it's going. I'm on the road, missing home, missing the road while I'm home, but baby, I'm going. With my heart on my sleeve, long nights and no sleep, rain, sunshine and snowing. I'm on the road, missing home, missing the road while I'm home, but baby, I'm going. I can't breathe, baby, I'm dying. Why are you crying while I'm trying for this love? I can't believe you think I'm lying. What are you not buying is what I'm trying now to know. This town's holding tight, but what you believe keeps you rolling. I'm on the road, missing home, missing the road while I'm home, but baby, this is my calling. There's no right line, just lies that keep this old train rolling. I'm on the road, missing home, missing the road while I'm home, but baby, I'm going. I can't breathe, baby, I'm dying.
ever been a cool hand Luke, the quarterback of the winning team, or the guy with the right kind of punchlines everybody wants to be. I never was that lucky old cuss with a straight flush in his hand, but with you, I am.
Hey everyone. All right, we're going to get started with our big, exciting lunchtime activity here. We're going to have a town hall discussion, and as many people as are in this room who wishes to should speak up and share their opinions on the topic. So we have I see a mixture of people here, and I hear some delicious country music in the background. Is there any way to kill that? Or is that outside? Is that outside? All right, thanks. All right. So, all right, for those who are kind of new to the field, if you will, meaning like within the last 5 to 8 years, roughly every decade, the National Academy of Science and Engineering and Medicine conducts a decadal survey for various communities, including ours, the heliophysics community. And we have this exercise coming up over the next couple years. Those of you who have been around for a long time know that there's a lot of studies and documentation, reports that are produced in various contexts by various groups, and you never know which ones are going to be impactful, right? Sometimes they bubble out later on, like the DAISY report, and become actionable items for the agencies. I can guarantee that the decadal survey is an important one. And so we as a community got to get this right. We have to get our actionable ideas integrated into this exercise. How many of you were not in the field in 2013? Okay, that's getting close to a third to half, right? So that was when the previous decadal survey happened. And let's see. So you need to be involved, okay? And you need to bring your good ideas to the table. So here's the overarching objectives of this session. Ultimately, where we're going, the vector we're heading to is producing an actionable set of recommendations for the decadal survey. And at this point, what that means is they have to be submitted formally in the form of white papers, again, for those of you who aren't aware of this. And we have, I guess I don't have the ability to click on my links in this form, right? But in the agenda, you can open up that second link rather, the working list of decadal white papers relevant to ground-based instrumentation and infrastructure. If you have the agenda on your device, that link is in there. And this is sort of where we've been collecting commitments from people and interest to join white paper teams around certain ideas. Information about what should be in a white paper is in that link there. I guess these slides can be distributed in some form, but that has all the information about the length and the FAQs of submitting white papers. So I'm just going to show just literally 2 more slides. I don't want to spend a lot of time talking. What we're targeting here ultimately is involving the NSF, either wholly or in partnership with another agency. That's kind of where this community should be focusing recommendations. The NSF has various funding constructs for infrastructure, from the small, which is sort of geospace section related, like the DAISY initiative, all the way up to MREFC, major research and infrastructure proposals exceeding $100 million. A good target for a community that might want to build a piece of infrastructure that could be shared by CEDAR, GEM, and maybe other interested parties, and has a solid science, cross-cutting science objective, would be the mid-scale proposals in the kind of $20 to $100 million range. So my question is, can we do something we've never done before in the CEDAR community? Can our community converge on a small number of priority recommendations? That small number, I think, ideally is 1. But let's just not, kind of look too far ahead. I also think, my opinion is that if we really want something to happen, it has to have convergence with other communities. So CEDAR, that should say, those two are already converged. The second one was supposed to be GEM. So ideas that converge CEDAR, GEM, towards things like geospace imaging, data assimilation, and system-level prediction, I think would be winners for the next decadal survey. And then other partners would join as well. And so, you know, I want to first of all thank Brian and Larissa and Asti for helping convene this session. We had a couple telecons, a couple Zoom calls where we tried to frame the session rather than come up with the answer to the challenge. And infrastructure categories could possibly be partitioned into 4 sorts of things: large monolithic facilities centered around 1 or 2 major instruments like a geospace radar or a whole atmosphere LiDAR or other things. A distributed facility, something like an inter-hemispheric chain of geospace observatories for doing system-level science. We could go all in on CubeSat constellations and formations in partnership with NASA. It's another kind of broad category of thing we can do. And then to make sure everything's covered, none of the above. Okay, so I think that, yeah, with that, what I'd like to do, if he's willing, is to turn this over to Alan for a few comments from the NSF perspective. You're going to go first? Oh, okay, sorry. All right, I guess Roman's going first.
No. Okay, thank you. So this talk is going to be a little bit more general. Decadal is an important tool and a process, but ultimate product of this community exercise and process is a facility or instrumentation tool. So this slide just summarizes in a bit more graphical form what Josh just presented in terms of individual programs that are available at NSF for new instrumentation. It ranges between going sort of from top to the bottom, individual proposals, major research instrumentation, mid-scale, and then major instrumentation. I'm going to talk a little bit more about major research instrumentation and mid-scale. And I also would like to talk about just space facilities program for various reasons. Just to give you a bit of background, the program has evolved over the years. It started with these large ionospheric radars or incoherent scatter radars. And currently we have 5, counting Arecibo as one of them. And we were able to add what we now call class 2 facilities, including daisies. So I'm just showing here daisies that are implementation or construction. I'm not showing design daisies that were also awarded back in 2019. And then we have all other class 2 facilities, including more recent ones, such as HARP or Auroral, Geophysical Observatory in Gakona, and extended Owens Valley solar array. So going beyond just CEDAR, just GEM, but also possibly SHINE. If you talk about major research instrumentation, MRI, there are, so if you're interested in developing the proposal, the submission window is early to mid-January. There are 2 proposal tracks, 100K to 1 million, and there is a limit of 2 per institution. And then track 2 is 1 million to 4 million, and there is a limit of 1 co-institution, and in that particular track, it's always a good idea to address local or not national impact of the instrumentation. There's a requirement of cost sharing of 30% for PhD granting and non-granting degree institutions, and there's no such requirement if, in fact, it's not allowed for non-PhD granting institutions. Over the years, Geospace section has done relatively well in this particular competition. Over the last 5 years, there were 7 MRI awards, 3 in astronomy, 1 in Mag, and 3 in STR. And this graph just shows sort of dollar amounts. And actually, if you count all other AGS, not just Geospace section, but atmospherical and Geospace sciences together, that's our division. Geospace accounts for about 55% of the total, which is really punching above the weight, because our budget compared to the total AGS is much smaller. It's something like 20% only. Going to mid-scale, there are 2 mid-scale programs, mid-scale 1 and mid-scale 2. Mid-scale 1 proposals are for design or implementation. Design projects could be between 600K and 20 million, and implementation projects between 6 million and 20 million. And the idea for the design is to prepare the project for the implementation. Then mid-scale 2 are implementation only. And I highlighted a couple of things here. These are supposed to be projects in a high state of project and technical readiness. They're supposed to be visionary and high priority national needs. So this is where the decadal process comes in. In terms of the timeline, we had 2 rounds of both mid-scale 1 and mid-scale 2. And 2 rounds for mid-scale 1 have been completed. We are in our 2nd round for mid-scale 2. Awards are likely to be announced this fall. There's no currently 100% certainty that there will be another round, but there is some certainty. And based on this time, we expect a letter of intent to be due in mid-scale 2, specifically early next year. There are some tips for making the best MSRI proposals. There are numerous solicitation-specific criteria here, in addition to the general NSF merit criteria of intellectual merit and broader impacts. Obviously, if you have a National Academy report that supports or prioritizes that particular project, that helps a lot. Also, it helps to emphasize the uniqueness of the project and to describe how that particular project is in high state of technical and project readiness. And that includes project management and things like life cycle of the project and possibly a divestment strategy. As with any NSF projects, broader impacts are very important. It's also important to include a direct training component, not just envisage student involvement somewhere down the line after the construction. And I want to finish with some thoughts that are a bit personal. As I said, the community has done relatively well in terms of MRI competitions. MSRIs are a different story. It's tough out there. It's highly competitive. We had no success so far. Other projects from other communities that have been successful had either entire or most community behind. So this is something that we should be striving for. The reason why there are numerous reasons why I wanted to involve also discussion of Geospace facilities program here is that O&M costs is one of them. What are they? Are they reasonable? is the program, is the only program that can support O&M costs, or there is something else? All these things are considered. So there are several things to discuss here that on a normal year, Space Facilities Program doesn't really have much room for new projects. We had a DAISY competition in 2019, and we were able to support existing facilities that do have certain innovation and vitality needs, and we've been able to do that last year, and we hope to do that looking forward. If you look through the years, you may also realize that most of the projects in the portfolio have not actually been started in NSF. We have either inherited certain large projects. So my predecessors have been really good in sort of identifying these opportunities and identifying the projects that perhaps look for a new home and whether they are a good fit for the program. And this is something that I think we should have in mind. And the other thing, the last thing, is that the program does not exist in isolation from other programs in the section and at NSF. So we work very closely. In fact, many of the awards that we were able to give recently would not be possible without contributions from other programs within the section. And I want to leave you with the following question. If mid-scale competition is going to be a challenge for the next few cycles, what is the community plan B? That's it for me, thanks.
While Alan's coming up, let me just make sure everybody understands that Roman mentioned O&M. Maybe everybody's not familiar with that, but you can build a facility, but you need a continuous annual operating budget, operation and management budget to keep it going, and that's a major concern. That's generally going to come out of your section. Yeah. And then you mentioned also that just a bit of context, and some of my ISR colleagues can probably provide more, but some of the big facilities that we've had in our community were kind of legacy facilities that were taken over by the NSF, not developed from scratch by the NSF. And I think that the AMISER program was the very first, right, that was sort of grounded directly in the NSF all the way through.
Yeah, there are lessons to be learned from the AMISER project. I'm not yet in a position to share these lessons.
Yeah, can I bring up my slides, please? Yeah, I'll be very quick. Just very top level to talk about the decadal survey again. So the decadal survey is funded by NASA, NSF, NOAA, and we all have common goals, but we also have somewhat different perspective. We have our statement of tasks to the academy. And for NSF, we have essentially the three requirements to the academy. One is, of course, the science priorities. That's the fundamental thing. And second is the infrastructure that can support science. And the third is the workforce development that can support science. So here today, we focus on the infrastructure part. And I just want to use this diagram, which are the response to the National Science Board in terms of mid-scale infrastructure needs. And the main message here is that you see the geo, which is the geoscience, has very large demand, okay, in this mid-scale infrastructure. So that's one indication that this proposal will be highly competitive, as Roman just mentioned. Okay, so the final thing is that for our discussion here for the community, the main message here is that for this mid-scale type of facility like AMISER, which is a very excellent example, is that we really need broad community support, buy-in. Okay, so Roman already mentioned that, And then I want to emphasize that, please realize this is certainly there are many different ideas. Josh already mentioned, could be a cluster, could be a network, could be other things. None of these are really in competition in terms of this decadal survey. Okay, so you should put your support behind any good ideas. The main idea is to put this into decadal survey. Hopefully it will finally get into the report. So you see my last message here. Essentially, that's what it is for, okay? So you want to have it in the decadal survey for it to have a higher chance to be funded once, the proposal is developed in the future, okay? So that's all. And I think next, Jared will also, from NASA, he will also talk a little bit from NASA's perspective, okay? Thank you.
So we have, apparently the internet went down, right? Oh, still down?
Oh, there he is. Okay.
All right.
Yeah.
So can I do a quick sound check? Can you hear me?
Yes.
Okay. So I'm just going to give a couple of comments about the NASA point of view. I don't have any slides. I can't overstate how important the decadal survey is. It is really the document that is recognized by our stakeholders. Whenever we want to bolster or grow our programs, a reference to the decadal survey is, shall we say, strongly expected. In the decadal survey, this coming decadal survey, we do have some goals. If you look at the statement of task, we've called out everything that we're looking for. And then there's additional material specific to NASA in the study approach document that accompanies it. We want to advance and expand the frontiers of the field. We want to go beyond what we've done in the previous decades and explore where else our science can apply, both purely scientifically, but also how it feeds into technology and operational activities like exploration and space weather. We want to focus on completable science investigations, things that can be completed in the next 10 years that enable large-scale advances and open new paths of investigation in the next decade and beyond. We want clear paths for collaboration with other agencies. NASA focuses on space, NSF is primarily ground, and NOAA does both. In the statement of task, we actually delineate the responsibilities for each agencies. We say that operational space weather activities go to NOAA. The recommendations regarding establishing new or supporting established ground-based observatories go to NOAA and NSF. And then spaceflight projects go to NOAA and NASA. By keeping those responsibilities clear, it helps us coordinate and better collaborate with each other moving forward. For NASA specifically, we're looking for recommendations for robust spaceflight programs. We want them to be healthy and sustainable. Part of that means the full range of mission sizes, not just the small explorers, not just the large missions in STP and LWS. Alan commented on the state of the profession. Please go read the information in the statement of task as well as in the study approach. NASA has been conducting some studies both with the national academies and internally. And what we're looking for the decadal survey to do is provide input on tailoring larger state of the profession issues to our community-specific concerns. For state of the profession in particular, but really for everything, no one expects the decadal survey to have all of the information. We don't expect the decadal survey to go, here is this problem, here's specifically how you solve it. We have constraints that we work within. There are other issues at play, things evolve. What is really most helpful from the decadal survey is providing background, context, the goals, where we need to get, and then the things that we need to keep in mind as we move there so that the agencies, I'll speak for NASA, so that NASA can take the decadal survey report, all that information, and plot out and plan actions to get to the recommended goals while still retaining the flexibility to adjust as we need to. And I will stop with that. Back to the room.
Jared, did you leave? I guess so.
Nope, I am still here. I just turned off my video.
Okay, thank you. Yeah. I just wanted to ask one question. I mean, you mentioned those the particular partnerships around different opportunities, and you had assigned, it seems like, all space flight ideas to NOAA and NASA. And I wonder if somebody could comment on whether or not we should even sort of, quote, waste our time thinking about NSF as a source for us or a partner for space flight missions. Maybe.
So I will let Alan speak to the scope of NSF. When we talk about spaceflight projects there, we are talking about the larger, in NASA parlance, the 7120.5, the large where we have the management insight and oversight of those projects. We're not referring to the smaller CubeSats, the smaller research activities there. Oh, and Alan just popped up on us.
Yeah, exactly, Jared. Yeah, thanks. So CubeSat at NSF is actually a large component of that is for education purpose, right? So many undergraduate students participate in this. That's a really important thing for NSF. But in terms of science and the decadal survey, the CubeSat doesn't last long, a couple years or some at most for those missions. So this is very different from the mid-scale infrastructure that we're talking about, like EMISR or others that will be there for on the decade scale. So yeah.
Okay, thanks. I appreciate it. Can we get some discussion started in the room? Any perspectives people want to share? You got a microphone coming your way. This is a question for Jared.
Yeah.
From
So, Jared, thank you for sharing your thoughts here. When I talk to more junior scientists, so sometimes I get the impression that more junior scientists are not entirely sure if they should also submit a white paper to the decadal survey, and quite often I also get the impression that they're not entirely sure how a good, impactful white paper possibly could look like. I mean, I understand that you can't really comment on behalf of the national academies because you are NASA, but I wonder if you can share any thoughts on that to clarify that. Thank you.
Of course. The answer is absolutely. The National Academies does not restrict submission of white papers to anyone. Whether you are a PhD student with an idea of where something needs to go, where a line of investigation needs to go, your early, mid, or late career, they treat everything the same. It's reasonable to expect that more senior people may have thoughts on more topics, but that does not diminish the value of anyone's viewpoint. With regards to white papers for the decadal survey, I can't give you a structure. I will say, one, there was a pre-decadal webinar where they talked about effective white paper writing. I don't have that handy. I will find the link and send it to Alan and ask Alan to distribute it to the CEDAR community. For the topics of white papers, they can be science, they can be state of the profession, they can be capabilities, whether it be computing or data archiving, how we handle open science, all of that's on the table. We want to hear everything. When you're structuring a white paper, and I'm trying to go quickly, when you structure a white paper, it is not an academic journal article. You do not get into the level of technical details. The best way to think about it is you are trying to convince someone of a viewpoint. And the way you do that is an honest conversation. Up top, you say, I'm going to tell you about X, why this is a problem, and why it needs a solution that looks like Y. Then you give a general background. X is this general topic. Here are the parts involved. And then you go into the background and describe enough detail with references as appropriate so that the individual, the reader, understands what you're getting at. And then you talk about, here's where the solution needs to go, here are the relevant issues, and here's an implementation that would work. These are short. I think Nazem said 7 pages for our decadal survey. So you don't have a lot of space. So it is a persuasive argument. It is not a technical, it's not a technical journal article. Does that help? I can't see the room. Was there any additional clarification that the room would like on that?
So Jared, I'm just going to jump in and add a little bit onto it from my previous experience having served on the decadal survey, and that is that every white paper is looked at by multiple people, and it's the quality of the ideas, the quality of the science that really carries through. So if you want to have an influence on the way the future of the field is going to go, get your ideas in there. Do it by yourself, form a coalition, do whatever you want, but get the ideas so they're part of their discussions. The other last piece that I would throw in there is think carefully about compelling graphics and compelling visuals that help tell the story, that can become part of the talking points in the presentation and this discussion. Because you're going to start off in a panel probably focused in on your particular things, but the idea has to carry forward all the way up through to the steering committee and beyond to communicate the compelling nature of the science and the questions to our field and the broader field, which is particularly important in the mid-scale research infrastructure lines and the infrastructure lines at NSF, because you're not just competing with the world of space physics, you're competing with LIGO, you're competing with TMT, you're competing with ideas to do cool physics problems, cool chemistry problems, cool social science problems. So you need to be able to communicate the compelling nature of the science to the broadest possible audience.
Thanks, Mike. That was Mike Wiltberger, used to be with the NSF, did a tour there.
So I just had a question about the white papers themselves as far as what happens after. So let's presume for a moment we get a white paper together, it gets accepted or whatever the process is. Is it in any way a commitment to then have to act on it, or is it then pushed back out to the community and the community acts on it? I don't understand that process.
Mike can start to address that one. That's a good question.
Yeah, right. So you're putting out an idea of something that you think that you want to have happen. It's not saying that you personally or your organization or your agency is going to do this. It's trying to get the community buy-in behind it so that the agencies can then act on it and do things with it as a compelling science question or a compelling science topic that needs to be resolved. So you don't need to run it through your sponsor research office. It's your idea.
Hi, I wanna, how about if you guys share an example of white paper? Probably that would be helpful. I don't know if that's possible. And another thing, once the community submits all the white papers, is it available to, like, can we see that later? Like what all white papers have been submitted? Or is it something only goes to NASA or NSF?
So I can give a brief reply to that. If you, the link to working white papers that is on the agenda, you can click on that, and some of them have already started to develop. Those are new white papers for this decadal survey. The previous ones I have asked, but it is not available publicly because they had server crash at national academies. But if anybody who has been around here, who has some access to previous white papers like Mike, please share.
The National Academy link that I showed up here includes in one of the tabs everything from the previous decadal. So your recommendation is to just cut and paste from that one to this one.
And the panel isn't established and the practices and what exactly hasn't been done yet, but you can look to the previous decadals for examples on this, and even more recently previous decadals like astronomy and astrophysics, that all of the white papers were then submitted to Frontiers Journal, got a DOI, were a publication, were traceable in that way. I think something similar to that may happen, and I'm going to hand the microphone to Phil to just jump in.
I'm just going to tell you that Joe Borofsky and a few of us are actually have issued a solicitation for papers exactly what Mike just said, because that way you get something that's citable and it's also now around for the next decadal survey in 10 plus years. So I would encourage you to make your work maybe work twice. It's not quite 1 for 2, it's 1 for 2 plus. But my point is that's available, and I highly encourage it. The people in astronomy have made very good use of that.
Yeah, we should make sure everybody's aware of that. I mean, I feel like we need to assemble some links and distribute them.
I will send it again to the CEDAR mailing list.
Yeah.
Just
Yeah.
to make sure it'll be open for a while.
So is there anywhere where we can see the what was accomplished in the current ongoing decadal survey? Like, where did we get to with it?
Oh.
So the easy answer to that is that actually there's the midterm assessment report that the National Academy conducted that actually goes back and does a mapping to the previous decadal and what was accomplished and makes recommendations for where to go for the thing of it. The midterm decadal for us actually ended up being a bit later. I think it was like 6 or 7 years into the process, so it's got a little bit more ground process to go into it there. Broadly speaking, a lot of what was recommended in that decadal survey was accomplished from small things that have had profound impacts, like the drive recommendations that have led to augmentations in NASA RNA funding to drive centers, to arguments for having something like the mid-scale at NSF, to the big missions from MMS to Parker Solar Probe to GDC kicking off. And so there's a lot of work that's been accomplished and achieved in there that's been done.
So looking at the list of white papers that have already been thought of, is it better to collaborate with a group that's already started or to start a new one? I guess my question is it quantity or is it quality of papers?
Well, Mike, do you want to take that one?
Somebody, yeah, I think the official answer is yes.
So I'm going to go
quantity
stand
and
up,
quality.
I'm going to go stand up next to Josh so that I don't have to keep handing the. This is just personal opinion from previous experience. I'm not on the academy, not on the survey and whatnot. Quality, I think, is really, really important more than quantity. I mean, yes, you can some of the comes in from it there, but remember that these are folks on that are on there. They're going to have to read every one of these things. Multiple people are going to read all of them, and so having to read the same thing over and over again isn't as important as the strength of the idea that gets conveyed. There is not necessarily more weight given to something that has 50 authors than something has 1 or 2. It really does boil down to the essence and quality of the idea that's in there. Josh, don't run away. I wasn't trying to drive you away.
No, but I mean, Mike has just a kind of an infinite experience having,
And for NSF, I can say this from my time there. It really does. Having that weight of the decadal survey really does matter in the discussions there, and I think it's going to be really important for the community to think through carefully in that competition for those very valuable mid-scale and MREFC dollars, and what you want to get out of that, what the community wants to get out of that. And I would really urge the innovation in the idea and the creative ways to go after what you want to do or in terms of accomplishing big science goals that comes into play there. Because you're competing with really, really different ideas from across the spectrum of science. I see somebody's got their hand up in the back.
Oh. Okay, while that is baking, I was going to ask maybe a little clarifying question here. I think we heard over the last day or two that, for example, the DAISY program, which has been going on and has been funded, isn't necessarily at the moment scheduled to continue. We've heard that Poker Flat is having major equipment problems and may not be here in a few years. So the question is, from the decadal survey point of view, should we be organizing additional white papers on the value of those existing assets in addition to new ideas. And so maybe our NSF folks would have an answer to that.
All right. So to what Mike was saying just like 1 second ago about reaching the widest possible audience, these are not going to be necessarily atmospheric physicists reading this, if I'm not wrong about that. So how should we introduce kind of some of the jargon that we're going to be using, and how fundamental should we be expected for these white papers?
Sorry, I thought I was going to answer Phil's question first. Okay, just to Phil's question first. For existing facilities, I think that's also still valuable to put that in the decadal white paper to argue, because of what we're talking about is, for the academy to recommend to us what are the infrastructure that needed to support the science. If the current infrastructure is needed in the future, that still, should be there. And in terms of our geospace support, I can say that we are very much committed to support these facilities in the future. AMISR, has some problem in the past, but I think that's mostly all kind of resolved, and they're moving the proper direction. So yeah.
On the white paper question, just there was
what's the
how fundamental we should be, that kind of thing. I mean, in general, everything has to at least have the appearance of precipitating from a strong, solid science question as a starting point. You should never try to convey a facility as a really good technical idea in search of a science mystery.
Yeah, but I think to respond to that, you don't have to, let's say, describe what ionosphere is. So you assume that the people who are reading your white paper on geospace science are going to be geospace scientists, like your peers.
We have a question in the back here. Is that okay?
I just want to comment about Poker Flat. Poker Flat is fine. I don't want to comment about Pfizer. But we've been here 53 years, and we should be here another 53 years at least.
Okay, so there's a question on Slido. Let me read the question. It's not there. So please describe SF response to ground-based facility recommendations in the last decadal survey and their commitment to take action based on the next decadal survey. Okay, so from the last decadal survey, there are many recommendations on quite a long list of facilities, and then we followed with the geospace portfolio review. So there are several actions taken follow the recommendation of that portfolio review. One example would be the creation of the DAISY solicitation, and also transition of some facilities, the Greenland, for example. Okay, so these are the things that NSF follow. So again, the decadal survey and portfolio review are all the things that NSF look at as from the committee recommendation in terms of NSF's funding priorities. Okay, and in the future, for the current decadal survey that come up in the future, certainly the decadal survey, again, we repeat it many times. It's a document that we look at very carefully, in terms of for guiding our future funding direction. So yes, so certainly we're committed to follow lots of this recommendation, but of course there's a resource constraint, and the mid-scale, again, is beyond the budget of the geospace science itself, so it's NSF-wide competition. Okay.
So I had a question about the actual decadal survey papers that for facilities. Is it only for discovery type science, or is it also for the ecosystem of instruments that need to be in place for other discovery science? So for example, you put up a new satellite system, we might need existing instrumentation to still exist to do CalVal and that kind of thing. It's not maybe as sexy as discovery science, but is that something worthwhile to put in a white paper?
Yeah, I think that also comes, actually in relation to the white papers on science. So my view is that the white paper, if it's more specific on what kind of infrastructure is needed, it can be based on, the science white papers, to say, okay, these are the science that community think are important, and then you can have a white paper specific on, okay, these are the infrastructure needed. And again, any infrastructure that support the science will be a good argument, but it will eventually up to the committees of the decadal survey to evaluate, to see what they can pick and choose, and to put that in the report. Yeah.
I want to say in general that's an excellent question. For instance, we always need a solar wind monitor at L1, right? I mean, that's been a big discussion in NASA community, and it's got such a kind of a multifaceted science mission that you wouldn't necessarily ascribe a single science question to it. And I think NSF, if I'm not wrong, should be thinking along those lines too. What do we need is continuous supporting infrastructure.
Yeah, well, I was just going to comment on the fact that not just necessarily from an NSF perspective, but this is the first decadal that has buy-in and participation from NASA, NOAA, and NSF. And NOAA is coming to the table in terms of some of those things that we think about as being the things that you need to just be able to fundamentally do our science, like a solar wind monitor. Are there other kinds of things that should be made part of the observational requirements for doing that could be picked up by NOAA to allow NSF and NASA resources to be pushing the boundary into the discovery space? And yes, is it an ecosystem of observatories, or is it one big thing? That's a great question, and thoughts that people have from the community and white papers on that, I think, would be very informative to the whole process. Yeah. That's it.
Yeah, that could have, 400 signatories to it. Right. I mean, a white paper like that, honestly, just the community needs this. I think there's a question.
So this is not a question, but basically a comment to the question Kumal, as a junior scientist, had basically to look into examples of white papers. So all the white papers that were submitted to the last decadal survey are public knowledge. And actually, if you go to the current decadal survey webpage at the National Academies, which you easily find if you Google it and you scroll down to the resources, there are actually links to every single white paper that was submitted to the last decadal survey. So you can read all 300-something white papers that were written 10 years ago.
Yeah, just quickly follow up, Mike's comment and all that. So even though we are CEDAR agronomy, the white paper to be impactful, reach out to other communities, right? Gem, Shine, and even beyond, about space weather, how to, also, meet NOAA's goals about space weather forecasting, and the NASA, of course. So that will be more impactful. Yeah, not just narrow agronomy questions.
So I guess my question is more at the strategic level, and thinking that since we now have 3 national agencies that are committed and on at the table for the decadal survey, what about other national agencies, and how does or how should the decadal survey nest within the national security policy, the national space policy, the national security space strategy, and all of those other documents that exist?
I can say something. Yeah. So on at the national level, there are laws or other executive orders, telling agencies to do this and that. Space weather would be one example, right? So I think a writing white paper referencing those will be also very helpful to justify the proposed actions or infrastructure support.
Yeah, I mean, I think there's a possibility of some connection there. Remember that the focus here is primarily on the research side of things, and so how the research could feed in potentially to a national security need or a national security requirement that comes into play would be worthwhile. And I do believe in the agency presentations that Julie Moses from AFOSR mentioned that AFOSR was thinking about joining on as a co-sponsor. So there may be some additional direction from the DoD perspective that comes in through that side of things, but I don't know the details on that.
On the previous decadal studies, both ONR and AFOSR chipped in a small amount compared to NASA, but they both contributed.
If there's no questions queued up, let me come back to a few things Roman said. I mean, he actually asked us some questions, and I would like to ask a question. When you say that we've been kind of unsuccessful with mid-scale, and my understanding is I think the primary reason that you mentioned was that the ones that won had a broader community backing it, and therefore the premise is that we need to do the same thing. We need to achieve that broad community. Part of my question is how big, how wide, how big is that stage? Is it CEDAR, is it CEDAR Gem, is it CEDAR Gem Shine, is it that kind of thing?
Ideally, it has to be the entire geospace community. And what you said makes a whole lot of sense. Just pick one. Just pick one project. Make sure that it's top-ranked project. You cannot really do that because it's national academies, but that's my view.
Okay. And then you asked about, let me just say, you asked about what the plan B is, and I would like to answer that by asking you, what's the plan B? But you can answer that later.
So I don't necessarily want to tell you what to do.
Go ahead.
But I think it has to involve the program, it has to involve the section, it has to involve a MISR lessons.
Okay.
It's just to this point that I'm not big facility operators and big outsider, but user of data. I mean, so I think it's a tricky. Maybe like if I really agree that we really need the big community support to go after a big opportunity like that, and we really need that. And then I was told that is really different from, for example, solar side. For example, the community get behind big mission and then make it happen, and that we really need that. We really need to get behind one big idea, but also it's true that CEDAR community's nature is many people have their own instrument idea and operate small instruments. So I wonder, like we are talking about for GDC dynamic and then Lotus idea, that rather than like dynamic against GDC against Lotus, that kind of thing, like let's go think big, that we really do transformative science. We win this together type of mentality, rather than like, okay, incoherent scatter radar versus DAISY. No, we need everything to advance our science. So rather than like, yeah, I agree that we have to get behind big idea, but big idea that includes everything. I don't know how you could formulate that. It needs a bit of coordination, I think. You could have multiple white papers, one big idea, but then other ideas well connected. Maybe that's one way to win together as a community for the next decade.
Well, as somebody in charge of both hemisphere and Mango, I support that idea. But speaking of lessons from hemisphere, and I think it's an extremely important point. One of the things that I'd like to bring up to the community here is we often don't have views into and understand what it takes to, say, run a facility. Operation and maintenance, when we say, if we are expecting, say, MISR radars, right, radars to provide support to GDC, it takes, how do you get from point A to point B to provide support for GDC? It's a lot that goes into that, and I think maybe this decadal survey is a time for us as a community to understand what it is and make sure that we actually put that sort of advocate for that sort of support for any facilities that we put in. So building a facility is one thing, but then making sure that it continues to get to the goal that we want to get to the goal is a separate thing. And so the decadal survey, I imagine, would also take in input for continuation of that sort of support if, as a community, we want it. I'm not saying that we should, I'm just saying that if we want it, we should think about that as well.
Can I ask a clarification for the young scientists in the room? What are the A-miser lessons that you referred to? I don't know what those are.
So I did say that I'm not yet in a position to share these lessons, but okay, I can start. If you think what happened, it took not one decadal, but two to make it happen. And it took quite a bit of earned leverage within NSF by Alan's and Mike's predecessors and my predecessors. If you think about it, it took all their earned respect and weight within the foundation to make it happen. I don't know if we are there.
Thank you.
With respect to these lessons learned from A-miser, we had a workshop about a year ago on the directions or strategy for the geospace facilities. During that, specifically for Raman, did we learn anything throughout that discussion during that brainstorm when I assume you got a white paper from that, or you had a white paper, have those lessons brought up during the white paper, and have we put strategies in place to overcome some of the difficulties we had and how to move forward, or we still trying to digest the information that we got from that workshop?
So this workshop, it's a good start. I believe the white paper is in the process of being well produced and submitted. I think I have seen that particular white paper on the list. There are other white papers in the same list. So the question to the community and eventually to the national academies, how that particular idea is going to be ranked against others. And I'm not sure if there's anything else here.
I guess we should revisit what we discussed in there and making sure that we have strong ideas that, as you said, will fare well with what the community, is going to be well aligned with the entire community, not only with people that are interested in doing new ISR measurements and things like that.
Yeah, thanks, Roman, and that's a good question. I mean, if you look at that report, it is an excellent report, but I also agree that it's a start, not really the final thing, because it actually wasn't a report that accomplished or conveyed community unity around a single idea or anything like that. It's sort of something that should accrete into that kind of document.
I have a quick question about, so talking about A-miser, incoherent scatter radar, those are big facility and then needs lots of resource. And then I remember that very exciting workshop that back in April. And then I wonder there's a white paper is one way to show the community support, but also this I've seen the GDC letters that being circulated, the collecting signatures, right? I mean, is there anything like that can be done for the large ground-based facilities that we all need data, right? I mean, from incoherent scatter radar, and then we need the longevity of those facilities to do all that all the science we like. So I wonder if there are anything that CEDAR steering committee and then the workshop committee have thought about. So that's a different way, right, I guess.
Yeah. Well, I would say that there's no, it's not like we have like too many people stepping up to lead. There's room for leadership, you know, if you're willing to help the community along. Everybody's invited to take a leading role. I would like to say I think we need to kind of wrap up, but I mean we can keep staying here, I guess, right? But when do the sessions be? 1:30 they start again?
Yeah, it's 1:30.
Yeah, I just want to make sure that I get in the comment that this was not meant to be sort of a complete conversation. It was meant to get it started, and we've got a few days left in the meeting. It's really fun to hash these things out in person, and so everybody should kind of go away from here and continue discussing. Yeah, Mike.
Sorry, I just wanted to say that time for conversation is running short, right? They've announced the chairs for the decadal survey. They've posted that online. I think in the next couple of months is going to be the deadline for the survey to get going. So you know, keep that in mind when you're having your discussions and moving forward. That it's time. You're really going to need to submit soon.
Yeah.
I just wanted to comment that there is a link here to the working list of decadal white papers, and we still have not had a chance actually to discuss specific white papers. So people declared their willingness to work on them, but I think as a community we still need to have time to talk. What are our suggestions? And I just wanted to point out, I just opened recommendations from the previous decadal survey, in particular recommendations about ground-based facilities. So what did rise to the top in the previous decadal survey? And some of these things that rose to the top, we really do not have them right now. Like some of it is a whole atmosphere LIDAR observatory, NSF medium-scale research facility program of the order of 40 to 50 million. Southern Hemisphere expansion of incoherent scatter radar, ionospheric modification facilities. So these were the things that were at the top of 10 years ago from the previous survey. What ideas are out there now, how different they are? We really have not had a chance to talk about it. And I think this specific meeting is maybe part of conversation, but we really need to talk about very specific things. And in a comment to Tomoka's question, and I think only when we decide and have maybe a short list of those ideas, then we can advocate for those ideas to really larger community and try to talk to work with other communities in earth science, maybe in magnetosphere and so on. But first we need to determine for ourselves what are our ideas.
I just want to reiterate what I have said, and that is a decadal is an important tool, but it's a tool. There are other things that are considered when evaluating, in particular, proposals to NSF.
Okay, so yeah, so I also have a quick comment. So indeed, there are lists of ground-based facility recommendations in the last decadal survey, but the reason that some of these are, well, many of them are not realized is not just because somehow the funding agency didn't do anything. I don't think many of those that put in the decadal survey actually result in any proposal to NSF. Okay, so I think there's a different phases here. The strategy is to try to come up with broadly supported ideas to put in white paper, put in the decadal survey. But that's just like Roman said, that's not all. Okay, so the next step, will be for the community to come up with really, executable plans, proposals that can go through the competition process. So these are two different things, right? So at that time, you will be talking about the specific implementation plan, technology, the cost, and everything, but that's not at this stage. For ISRs, there are also many different ideas, right? But that's I think, you don't want to hand up too much on that. You want to do, the A-miser type or single dish. These are, at a bit lower level than the science. Okay, ISR can do similar things. Maybe there are some different capability, but that's certainly very different from optical instrument. So what kind of thing they can do to help the science? That's, I think, need to be focused on that. Okay.
Thank you. I just want to make a comment about, I think, for example, a Carrington effect problem, right, happens every 200 years or something like that. And if it happens, are we prepared to address these problems? Are these, a Carrington problem encompasses many fields. Are these topics things that we should pursue in the decadal survey?
Yeah, so again, these are the questions that the community need to answer. What science questions are important that we need to, so it's not for the agency to say, okay, you should answer this question. Okay, so that's exactly the point of the decadal surveys, for the community to tell the agencies what are the questions.
Okay, so I'm asking the community then, right. Is it a question should pursue? This is a problem, should we be pursuing? And that's one question. The other suggestion is that I didn't participate on the previous decadal survey, and right now there is momentum to do that. I would suggest to keep doing this every year at CEDAR. I think it's nice to have this, so we are prepared for the next one. So.
So Josh, I don't know how much time we have before people, fall down from hunger. So in the interest of time, like Mike said, there is not a lot of time. I would please urge you to go to this link of working list of decadal white papers. These have come after at least 3 workshops that were held in support from NSF and NASA in the CEDAR and GEM community, plus the Helio 2050 effort that some of you may know that happened last year. There are people who are listed as leaders of these white papers with their email addresses. If you're interested in contributing to this white paper, please reach out to them and add new white papers, topics with your name, email, so other people can reach out to you. There is, of course, need to keep talking more to have, create a curated list of things that we would like. And so if you want to, for example, create a workshop for that, please send an email to CEDAR listserv and set up a time to do that so people can join. But yeah, I think this is a really good starting point to get started and maybe do something good. Josh?
Yeah, I think we'll wrap it up there. And like I said, let's keep discussing.
My last question, thank you. My last question is really concerned about timing. I think Mike said that we decadal white papers, so it will open soon. And you said 2 months. We can expect 2 months to complete it. That seems to be really short. Can you comment more on this? Can we expect? So what actually community can expect?
So again, I'm not speaking in any official capacity. I'm not tied to the thing. I'm just talking about what the Academy folks have been saying is they've been going to meetings for a while and telling you the white paper deadline was going to come on, and then what the process was in the astronomy side was the call finally came out, and it was 2 months after the time frame that the call came out that the white papers had to be done. So you need to be working on your white papers now so that they're ready to go for submission.
Yeah, that is what other people who supported this effort told, that it's going to be 2 months from the time they announce.
So that deadline begs the question, and I don't know who can answer this, but who is the deciding authority on which white papers get pushed forward? And how does that process actually happen? Because if we keep saying we, the community, are the deciding authority, it's never going to happen. So is it the steering committee? Who is it?
Decadal Survey Steering Committee, in collaboration with these individual panels in various specialized areas. So there's a kind of a hierarchical structure around creating the Decadal Survey. And you heard the comment that all white papers are reviewed, no matter how many there are. I believe that is the case. That was borne out in what happened with the last Decadal Survey.
So none are rejected at all? It's like everything gets pushed forward?
Yeah, so you should submit everything.
Yeah, Diana, so as far as we discussed, so we do not decide, we do not rank this, our community doesn't rank these white papers, but Decadal Survey Committee looks at all the white papers. But I think the idea for us is really to still to discuss all the ideas that come from community and maybe build our support behind some of those ideas.
I think it might be helpful to understand a little bit more of how the committees are formed. So currently, the co-chairs are selected, but even that co-chair, I think, is not finalized. It's waiting for community input. Okay, so once the co-chair is selected, and co-chair will construct the steering committee, and then there will be panels. There will be still more time that they need to form the entire group that doing the review. And at the same time, of course, please work on the white paper. And then after that, I think they will announce the deadline, right? Or maybe earlier.
The deadline will be coming the announcement of the deadline will be coming very soon, prior to the final formulation of the panels and whatnot, because they want the papers to be in place, so at the first meeting of the panels that happens, they have material input to review. So it's coming very soon.
And from what I understand, at least Shine community is very, very well organized. They have already been working on several white papers on multiple issues, meeting every week. So we need to sort of catch up.
All right, thank you all. Happy to chat with anybody.
Yeah.
This session or any of the Decadal issues.
gonna set aside my pride. Not gonna be the one to say goodbye. Well, neither am I. Oh, tonight we're gonna set the world on fire. And I'm gonna set aside my pride. Not gonna be the one to say goodbye. Neither am I. Oh, tonight. She's as free as blue bonnets in the summer. She's as hot as the Padre Island sun. And most of the time she's as warm and friendly, like the hills that surround Austin. She's as bright as the Dallas sky. She always holds her head up high. She loves the company of her family. She has faith in God's greater plan. She trusts I'm a good man, and that's why I'll always believe. She's like Texas, and she likes me. Her eyes are green like the trees in Nacogdoches. Her teeth are white as cotton in the fall. And when she laughs, you'll always take notice, 'cause her heart's charm will shine right through it all. She's as bright as the Dallas sky. She always holds her head up high. She loves the company of her family. She has faith in God's greater plan. She trusts I'm a good man, and that's why I'll always believe. She's like Texas, and she likes me. Change like the weather out in Lubbock, but if you show her love, man, she'll return it. She's as bright as the Dallas sky. She always holds her head up high. She loves the company of her family. She has faith in God's greater plan. She trusts I'm a good man, and that's why I'll always believe. She's like Texas, and she likes me. Oh, she's like Texas, and she likes me. chase that Chattanooga freight. Couple of kids in a Chevrolet. Catch a little air when we cross the tracks. Sipping on something from a paper stack. You hang your shirt on that maple limb. Slipping through the moon to the river bend. Wasn't very long, I was jumping in. I guess I'm still doing now what I was doing then. Chasing you like a shot of whiskey. Burning, going down, burning, going down. Chasing you like those goodbye tail lights. Headed west to anywhere out of this nowhere town. Chasing that freedom, chasing that feeling that got gone too soon. Chasing that you and me, I only see in my review. Till I'm laying here tonight, holding someone new. Still chasing you, still chasing you. You always used to talk about LA. I heard you got as far as Santa Fe. Well, you know I tried to track you down. I only got as far as Guitar Town. Singing about a girl I used to know, used to know, used to know. That I haven't given up, I'm just on your radio. Chasing you like a shot of whiskey. Burning, going down, burning, going down. Chasing you like those goodbye tail lights. Headed west to anywhere out of this nowhere town. Chasing that freedom, chasing that feeling that got gone too soon.